Imagine a place where the laws of physics bend and twist, where stars are born from chaos and celestial bodies dance in mysterious orbits. Our universe is filled with these remarkable anomalies, defying our understanding and beckoning us to explore. From the enigmatic behaviors of black holes to the whispers of dark matter, these cosmic phenomena challenge us to reconsider everything we think we know. Join us as we delve into some of the most fascinating anomalies in space. The universe is filled with wonders, many of which remain tantalizingly mysterious even to the most knowledgeable scientists. One of the most puzzling phenomena is dark matter. While it is thought to make up almost 25% of the universe, it does not emit, absorb, or reflect light, making it incredibly elusive. Astronomers have inferred its existence through its gravitational effects on galaxies and cosmic structure, but its true nature remains one of the biggest unsolved questions in cosmology. Another enigmatic feature of the cosmos is dark energy. This mysterious force appears to be driving the accelerated expansion of the universe. Although it accounts for about 70% of the universe, scientists do not fully understand what it is. Some theories suggest it could be a property of space itself, while others entertain the possibility that it is indicative of new physics beyond our current theories. Dark energy is at the heart of many debates and research efforts, pushing the boundaries of our understanding of the cosmos. Then there are fast radio bursts, short bursts of radio waves from deep space that last only a few milliseconds. Discovered in the last few decades, these intense bursts are one of the most exciting discoveries in contemporary astronomy. Their origins are still a mystery, with theories ranging from colliding neutron stars to the activity of alien civilizations. Each new fast radio burst detected adds to the intrigue and raises questions about the nature of cosmic phenomena. Lastly, we have gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. These bursts can release more energy in a few seconds than our sun will emit in its entire 10 billion-year lifespan. While we understand that they are associated with the collapse of massive stars or the merging of neutron stars, many details about them remain unclear. What triggers these immense explosions? How do they behave and interact with their environment? The universe continually surprises us with such profound mysteries, inviting both awe and inquiry into its deeper workings. Black holes are one of the most fascinating and enigmatic phenomena in the universe. They challenge our understanding of physics, particularly the theories of general relativity and quantum mechanics. At their core, black holes are regions of space where the gravitational pull is so intense that nothing, not even light, can escape. This powerful gravity comes from the collapse of massive stars, compressing their mass into an incredibly small point known as a singularity. Here, our traditional understanding of physics breaks down, leading us to question what we know about space, time, and the very nature of reality. As we explore the implications of black holes, we encounter the idea of time itself behaving differently near them. According to Einstein's theory of relativity, time is not a constant. It can stretch or compress depending on gravity and speed. Near the event horizon, the boundary around a black hole, time appears to slow down dramatically for an outside observer. For someone falling into a black hole, however, they would not notice this difference. Such peculiarities challenge our intuitive grasp of time, illustrating how it is intricately linked to the fabric of the universe. Moreover, the nature of the singularity poses another serious challenge for physicists. Here, our current models of physics cease to function. Understanding what happens at this point could unlock new realms in scientific thought, potentially bridging the gap between general relativity and quantum mechanics. This intersection is considered one of the greatest unsolved problems in modern physics, because if we can decipher the secrets of black holes, it may redefine our understanding of the universe itself. In seeking to comprehend black holes, researchers are pushed to rethink fundamental concepts. The study of black holes encourages us to question established truths and to dream about possibilities beyond our current knowledge. Their existence suggests that our universe is far more complex and surprising than we could ever have imagined, beckoning us to continue our quest for understanding the cosmos. Dark matter is a mysterious and elusive substance that makes up about 27% of the universe. Unlike ordinary matter, which forms stars, planets, and everything we can see, dark matter does not emit, absorb, or reflect light. This makes it invisible to our instruments. We cannot see it directly. However, its presence is inferred through its gravitational effects on visible matter, particularly in how galaxies rotate and cluster together. When astronomers observed galaxies, they found that the stars on the edges were rotating much faster than expected based on the visible mass alone. This discrepancy suggested that there must be something else exerting gravitational influence, holding these galaxies together. Dark matter, acting as this unseen glue, keeps the cosmos from unraveling. Furthermore, studies of cosmic background radiation have revealed that the structure of the universe is consistent with the existence of this hidden mass. Understanding dark matter is critical to our conception of the universe. It plays a significant role in the formation and evolution of galaxies, influencing their shapes and the distribution of galaxies across vast cosmic distances. Without dark matter, our current models of cosmic structure would fall apart, leaving significant gaps in our understanding of how the universe has evolved over billions of years. Beyond its impact on galaxies, dark matter offers clues about fundamental physics. It challenges our understanding of matter and interaction, pushing scientists to explore theories beyond the standard model of particle physics. As researchers continue to hunt for direct evidence of dark matter, its true nature remains one of the universe's greatest puzzles. Each discovery in this ongoing quest enhances our comprehension of reality itself, showing that what we thought we knew is often just the tip of the iceberg. Dark energy is one of the most intriguing and mysterious components of our universe. It is a form of energy that makes up about 70% of the universe's total energy content. Unlike matter, which can be seen and measured, dark energy does not emit light or any form of radiation, making it invisible and difficult to detect directly. What we do know is that it has a profound effect on the universe's expansion. To understand dark energy, we need to consider the cosmos's structure. When astronomers observed distant galaxies, they found that not only were these galaxies moving away from us, but they appeared to be accelerating in their retreat. This unforeseen acceleration suggested that an unseen force was driving this expansion. This led to the hypothesis of dark energy, a repulsive force acting in opposition to gravity. While we can't directly see dark energy, its influence is clear in the way galaxies behave at great distances. The implications of dark energy are vast. If dark energy continues to drive the acceleration of the universe, it could lead to a future where galaxies drift far apart, beyond our ability to observe them. This scenario, often termed the Big Freeze, would transform the universe into a cold, dark expanse with galaxies fading from view. Essentially, it raises profound questions about the fate of the cosmos and the ultimate destiny of all matter in it. Ultimately, dark energy compels scientists to rethink fundamental concepts about gravity, space, and time. It beckons us to explore further, pushing the boundaries of our understanding of physics and the universe. Each discovery about dark energy not only illuminates the mysteries of the cosmos, but also deepens our appreciation for the complexity and wonder that permeates the universe we inhabit. Neutron stars are one of the most extraordinary objects in the universe, drastically different from the regular stars we usually think of, like our Sun. While ordinary stars shine by fusing hydrogen into helium, neutron stars are the remnants of massive stars that have exploded as supernova. What remains is an incredibly dense core, mostly composed of neutrons, which are created when protons and electrons combine under the immense gravitational pressure of the collapsing star. This process leads to an object so small, typically only about 20 kilometers across, yet more massive than our Sun, resulting in an incredibly high density. A sugar cube-sized amount of neutron star material would weigh about the same as a mountain. One of the most fascinating aspects of neutron stars is their rotation. After the supernova explosion, the conservation of angular momentum causes these stars to spin at astonishing speeds. Some neutron stars can complete a rotation in just milliseconds. These rapidly spinning neutron stars are known as pulsars and emit beams of radiation from their magnetic poles. As the star spins, these beams sweep through space, and if they happen to point towards Earth, We see them as regular pulses of light, much like a lighthouse. This regularity allows astronomers to use pulsars as cosmic clocks, offering insights into fundamental physics. Neutron stars also showcase some bizarre anomalies, particularly in their magnetic fields. They can possess magnetic fields over 1 trillion times stronger than that of Earth, which can lead to unique phenomena. Some neutron stars, known as magnetars, are characterized by their exceptionally powerful magnetic fields, which can generate intense bursts of X-rays and gamma rays. These bursts are precipitated by rearrangements in the magnetic field, producing energy levels that dwarf those of regular stars. Moreover, the study of neutron stars helps scientists understand the behavior of matter under extreme conditions, where the laws of physics are pushed to their limits. The interactions within neutron stars challenge our understanding of nuclear forces and density, creating a miraculous environment ripe for research. Each discovery leads to more questions about the fabric of the universe, revealing just how varied and strange the cosmos can be beyond our own familiar starry night. Pulsars are a fascinating type of celestial object, categorized as highly magnetized, rotating neutron stars. These stellar remnants form when massive stars exhaust their nuclear fuel and collapse under their own gravity, leading to an explosion known as a supernova. The core that remains is incredibly dense, so much so that a sugar cube-sized amount of material from a neutron star would weigh as much as an entire mountain on Earth. As these neutron stars spin, they emit beams of electromagnetic radiation, which can be detected as regular pulses from Earth, much like the beam from a lighthouse sweeping across the ocean. The significance of pulsars in the study of the universe cannot be overstated. First and foremost, they serve as precise cosmic clocks. Their rotation is incredibly stable, allowing astronomers to use them to measure time with remarkable accuracy. By studying the timing of these pulses, researchers can glean invaluable information about the behavior of matter under extreme conditions, including the nature of gravity and the extremes of nuclear physics. Moreover, pulsars have opened up exciting avenues for research in both astrophysics and fundamental physics. One of the most groundbreaking discoveries involving pulsars was the detection of gravitational waves. When two neutron stars orbit each other, they create ripples in the fabric of space-time. By observing changes in the timing of a pulsar's signals caused by these waves, scientists can confirm the existence of phenomena proposed by Einstein's theory of general relativity. Additionally, pulsars have acted as cosmic laboratories, helping to probe the interstellar medium, the matter that exists in the space between stars. By analyzing how pulsar signals change as they pass through this medium, researchers gain insights into its composition and characteristics. All in all, pulsars are not just captivating cosmic objects, but also vital tools for unraveling the mysteries of our universe and the fundamental laws that govern it. Cosmic rays are high-energy particles that travel through space and, remarkably, can originate from some of the most energetic and powerful events in the universe. These particles include protons, atomic nuclei, and heavier elements, hurtling through the cosmos at almost the speed of light. When these cosmic rays reach Earth, they interact with our atmosphere, creating a cascade of secondary particles that scientists can detect. This interaction helps researchers decode the origins and nature of these high-energy cosmic phenomena. Understanding cosmic rays allows scientists to gain insights into extreme events such as supernova explosions, black hole formations, and gamma-ray bursts. For instance, a supernova can produce a tremendous amount of energy, propelling cosmic rays into space. By studying these cosmic rays, particularly their energy levels and composition, scientists can piece together the mechanics of such explosive events. This information serves as a vital clue to understanding how matter behaves under such extreme conditions. Moreover, cosmic rays act as messengers that carry information from distant galaxies and regions beyond our solar system. By analyzing their energy patterns, researchers can glean details about the environments from which they originated, allowing them to map out the structures and dynamics of our universe. For example, the highest energy cosmic rays observed are believed to be associated with some of the most powerful astrophysical sources, including supermassive black holes and the remains of supernova. In short, cosmic rays significantly enhance our understanding of high-energy events in the universe. By tapping into these particles and their interactions, scientists not only reveal aspects of the cosmos we might not see otherwise, but also deepen our comprehension of the very nature of the universe itself, its origins, evolution, and the forces that govern it. Astronomers have been fascinated by spiral galaxies for decades, studying their graceful arms and vibrant features. Among the most unusual discoveries is the presence of trailing spiral arms that twist in unexpected ways. Instead of being uniformly structured, these arms can show intricate patterns, often resembling a feather's delicate filigree. This complexity suggests that the dynamics of star formation and gravitational interactions play a significant role in shaping the galaxy's structure. Another striking feature observed in some spiral galaxies is the existence of barred spirals. In these galaxies, the traditional spiral arms are interrupted by a central bar-like structure. This bar is more than a visual curiosity. It influences the movement of gas and stars within the galaxy. As they orbit, the bar can funnel gas into the central region, stimulating bursts of star formation that can illuminate the galaxy's core, giving it an unusual brightness and activity. Some spiral galaxies also display regions of intense star formation characterized by luminous blue clusters. These clusters are often the result of dense clouds of gas collapsing under their own gravity, creating new stars at an astonishing rate. This violent process can lead to supernova explosions, sending shockwaves through the galaxy and triggering even more star formation, which adds to its dynamic nature. Lastly, astronomers have noted peculiarities such as ringed spirals, where concentric rings of stars and gas orbit the galaxy's center, creating a striking visual effect. These rings can indicate complex evolutionary histories, possibly caused by interactions with nearby galaxies. The study of these unusual features not only deepens our understanding of spiral galaxies, but also reveals the diverse and dynamic nature of our universe. Gravitational lensing is a fascinating effect predicted by Albert Einstein's theory of general relativity. It occurs when a massive object, like a galaxy or a cluster of galaxies, lies between an observer and a more distant source of light. The gravity of this massive object bends the light from the distant source, much like a convex lens focuses light. This bending not only magnifies and distorts the appearance of the distant galaxies, but can also create multiple images of the same galaxy. This phenomenon acts as a cosmic magnifying glass, allowing astronomers to see galaxies that would otherwise be too faint or far away to detect. By studying these distorted images, scientists can gather valuable information about the distant galaxies, including their shapes, sizes, and estimated distances from Earth. This data helps in unraveling the properties of dark matter, a mysterious substance that plays a critical role in shaping the universe but cannot be observed directly. The distribution of dark matter can often be inferred from how it distorts the light of more distant galaxies. Gravitational lensing also provides a unique way to study the expansion of the universe. As light travels through the cosmos, it may encounter various gravitational fields, and tracking how light is bent by these fields can reveal the rate at which the universe is expanding. This helps astronomers better understand cosmic events over billions of years and shed light on the history and nature of the universe itself. Gravitational lensing is not just a curious optical effect, it is a powerful tool in modern astronomy. It opens the window to the distant universe, revealing the structure and evolution of galaxies that formed when the universe was much younger, all while deepening our understanding of the fundamental forces at play in the cosmos. The cosmic microwave background radiation, often referred to as the CMB, is one of the most significant pieces of evidence supporting the Big Bang theory. It is the afterglow of the hot plasma that filled the universe when it was just 300,000 years old. Although it appears quite uniform across the sky, astronomers have discovered intriguing anomalies in the CMB that challenge our understanding of the cosmos. One notable anomaly is known as the cold spot. This area in the CMB is significantly cooler than its surroundings and has sparked much debate among scientists. Some researchers propose that this cold spot could be a sign of an enormous supervoid, an immense region of empty space stretching over 1 billion light years. Others suggest it might indicate the presence of structures or phenomena that remain poorly understood, possibly hinting at new physics or even alternate theories of the universe's evolution. Another fascinating feature is the alignment of the CMB's temperature fluctuations with the large-scale structure of the universe. Specifically, some regions in the CMB appear to be unusually aligned, which raises questions about chance. This alignment suggests that the universe's structure is not entirely random, yet what causes these correlations remains a mystery. Some scientists speculate that they might be related to the effects of gravitational waves from the early universe or other unseen factors at play during cosmic inflation. The existence of these anomalies invites us to explore beyond our standard cosmological models. They challenge what we think we know about the universe's formation and evolution, prompting exciting questions about dark matter, dark energy, and the very fabric of space-time. As we continue to study these features, we may uncover deeper insights into the universe's history and its ultimate fate, reinforcing the notion that our cosmic journey has just begun. The concept of the multiverse, which suggests the existence of multiple, perhaps infinite universes beyond our own, has fascinated scientists and enthusiasts alike. Several compelling theories have emerged to frame this intriguing idea, each rooted in different aspects of physics and cosmology. One of the most talked about theories is derived from quantum mechanics. It proposes that every time a decision is made or an event occurs with multiple possible outcomes, a new universe is created for each possible outcome. This is known as the many worlds interpretation, and it presents a reality where every path taken, and even those never taken, exists simultaneously. Another prominent theory arises from cosmic inflation, a period of rapid expansion that occurred just after the Big Bang. According to this theory, different regions of space may have stopped inflating at different times, leading to bubbles that form distinct universes with varying properties. Each of these universes could possess different physical laws, constants, and dimensions. This inflationary multiverse concept extends our understanding of the cosmos beyond the single universe we observe, suggesting that our universe is merely one bubble in a vast sea of others. A third intriguing perspective comes from string theory, which attempts to unify all fundamental forces of nature. In string theory's landscape, there are a vast number of possible configurations for the universe, each leading to different physical laws and constants. This speculative framework hints that every set of physical rules we see in our universe could represent just one possibility within a broader multiversal framework. As researchers delve further into string theory, they continuously uncover new insights that could support the existence of a multiverse. Finally, the anthropic principle adds a philosophical layer to the discussion. This principle posits that the specific conditions we observe in our universe must permit the existence of conscious observers like us. Therefore, among countless universes with different physical laws, we find ourselves in one that allows for life, making our universe seemingly fine-tuned for human existence. Each of these theories invites us to ponder profound questions about the nature of reality and our place within it. The multiverse concept opens a dialogue about existence that pushes the boundaries of our understanding and invites wonder at the complexities of the cosmos. String theory has emerged as a fascinating potential framework that seeks to unify the fundamental forces of nature. At its core, string theory proposes that the very building blocks of the universe are not point-like particles, as traditionally thought. Instead, it suggests that they are tiny, vibrating strings. These strings can oscillate at different frequencies, and the way they vibrate determines the properties of the particles we observe, such as mass and charge. By shifting the focus from particles to strings, this theory offers a fresh perspective on how the universe is structured. It hints that the forces of nature, gravity, electromagnetism, and nuclear forces, might be manifestations of one underlying reality. String theory also opens the door to the idea that there are additional dimensions beyond the familiar 3 dimensions of space and one of time. In fact, some versions of string theory suggest that as many as 10 or 11 dimensions may exist, intricately woven into the fabric of the universe but eluding our direct observation. One of the most striking contributions of string theory is its potential to reconcile gravity with quantum mechanics. These two pillars of modern physics have long been at odds. While quantum mechanics successfully explains the behaviors at the smallest scales, general relativity describes gravity and the cosmos at vast scales. String theory aims to bridge this gap, offering a way to understand gravity in the quantum realm, which could unveil deeper insights into the nature of black holes, the Big Bang, and the fundamental structure of space-time itself. Despite its beautiful concepts, string theory remains largely theoretical, with many predictions yet to be tested experimentally. However, it has sparked a wealth of research and thought, influencing various fields in physics and mathematics. As scientists continue to explore its implications, string theory could reshape how we perceive the universe, transforming it from a collection of particles into a rich tapestry of strings, woven together in ways that we are only just beginning to understand. Wormholes, often referred to as bridges through space and time, are a fascinating concept in theoretical physics. Imagine a tunnel connecting two distant points in the universe. Instead of traveling across the vast emptiness of space, which can take millions of years, a wormhole would allow for instantaneous travel between those two locations. This challenges our traditional understanding of space by suggesting that distance can be fundamentally altered through these hypothetical shortcuts. The implications of wormholes extend beyond mere travel. They shake the very foundations of how we understand the fabric of the universe. If wormholes exist, they challenge the notion of a linear model of time. Picture this: traveling through a wormhole might not only take you to a different place, but also a different time. This raises tantalizing questions about causality and the nature of time itself. Could someone travel back to witness historical events or potentially alter the course of history? Moreover, the existence of wormholes could shed light on the mysteries surrounding black holes. Inside black holes, where gravity is overwhelming, space-time behaves in ways we still struggle to comprehend. Some theories propose that black holes could be linked to wormholes, creating potential exits in other parts of the universe. This tantalizing notion suggests that deep in the cosmos, there might be connections that we cannot yet observe, raising the possibility of interaction between entirely separate regions of space. Yet, despite their allure, wormholes remain purely theoretical. Current physics does not provide a concrete way to create or stabilize such structures, as they would require exotic forms of matter with negative energy density, which we haven't found. Nevertheless, the exploration of wormholes encourages us to transcend our current understanding, pushing the boundaries of what is considered possible and inviting us to ponder the vast, mysterious universe in new and profound ways. The hypothesis of a cyclic universe presents a fascinating perspective on the nature of our cosmos. This idea suggests that instead of a singular beginning followed by perpetual expansion, the universe undergoes an endless series of cycles. In each cycle, the universe expands from a Big Bang, eventually reaches a maximum size, and then contracts back to a hot, dense state, paving the way for another Big Bang. This model challenges the traditional view of a linear timeline, where the universe has a clear origin and a projected end. In exploring this hypothesis, we must consider what it means for our understanding of time and existence. If our universe is part of an eternal cycle, then concepts of beginning and end become less relevant. It turns the narrative of a cosmic history into one of recurring patterns, where each cycle could potentially reset the stage for new physical laws or conditions. This perspective opens intriguing questions about the nature of time itself and whether time is truly linear or something more complex. Additionally, a cyclic universe prompts us to reconsider the implications for life and consciousness. If the universe has existed in various forms throughout infinite cycles, this raises inquiries about the permanence of actions and events. In a sense, past universes might influence the conditions of the present one we inhabit, thereby blurring the lines between different epochs of existence and inviting us to contemplate the nature of our reality. Embracing this hypothesis is not just an academic exercise, it invites deeper philosophical reflection about our place in an ever-evolving cosmos. While the cyclic universe theory is still under active research and debate in the scientific community, it challenges us to think beyond the confines of a static universe and embrace a more dynamic view. The idea that we might just be one chapter in a much larger unfolding story can leave us with a sense of wonder about the universe and our connection to it. Theories of quantum gravity represent a fascinating frontier in our understanding of physics, particularly when it comes to black holes. Traditionally, black holes have been viewed through the lens of general relativity, which posits that these cosmic entities are formed when massive stars collapse under their own gravity. This perspective suggests that once something crosses the event horizon, a point of no return, it is lost to the universe forever. However, the arrival of quantum mechanics into the discussion shakes this foundation. Quantum gravity attempts to unify general relativity with quantum mechanics, which deals with the behavior of particles at the smallest scales. One of the most striking implications of this merger is the idea that information, which can be thought of as the very essence of physical states, cannot be destroyed. This challenges the notion that anything falling into a black hole is irretrievably lost. According to quantum principles, there must be a way for this information to be preserved, leading to what is often referred to as the black hole information paradox. Some theorists propose that instead of completely vanishing, information may be stored on the event horizon itself, a concept known as holography. This suggests that the three-dimensional information about items that fall into a black hole is encoded on its two-dimensional surface. Even more intriguingly, some researchers have suggested that black holes might not even be entirely black. They could radiate particles, a phenomenon called Hawking radiation, which again implies the potential for the escape or transformation of information. Thus, the interplay between quantum mechanics and black holes challenges our classical understanding. It suggests that the reality of black holes is far more complex than once thought, inviting us to reconsider what we know about the fabric of the universe. As scientists continue to explore these ideas, our comprehension of black holes and the fundamental rules that govern the cosmos may evolve in ways we can hardly anticipate. Chaos theory plays an intriguing role in the field of cosmology, particularly when it comes to predicting cosmic events. At its core, chaos theory examines how small differences in initial conditions can lead to vastly different outcomes. This unpredictability is aptly summed up by the concept of the butterfly effect, where the flap of a butterfly's wings in one part of the world might set off a tornado in another. In the cosmos, this principle manifests in various ways, particularly in the behavior of planetary systems and the dynamics of galaxies. One area where chaos theory significantly contributes is in the modeling of planetary orbits. These are not always stable, as they can be influenced by gravitational interactions with other celestial bodies. When these forces come into play, tiny changes can spiral into enormous shifts over time, making long-term predictions about the positions of planets quite complex. For instance, a seemingly minor shift in one planet's orbit can lead to substantial changes in the entire system over millions of years. Moreover, chaos theory influences our understanding of stellar evolution. As stars age and their processes change, they can be pushed into different paths by seemingly small variations. This aspect is crucial when studying phenomena like supernova explosions or the creation of neutron stars and black holes. The chaotic behaviors that arise in these circumstances challenge our ability to predict exactly when or how such events occur, rendering some cosmic predictions inherently uncertain. While chaos theory suggests inherent unpredictability in cosmic events, it also underscores the beauty and complexity of the universe. This interplay between order and chaos invites scientists to explore the fundamental rules that govern celestial mechanics, pushing the boundaries of our understanding. As cosmologists continue to unravel these complex threads, they embark on a journey full of surprises and new discoveries, illustrating the boundless wonder of the cosmos. Simulations of alternate universes serve as powerful tools for scientists who seek to unravel the mysteries of our own universe. By creating various theoretical models, researchers can explore how different conditions, laws of physics, and initial parameters might lead to completely different cosmic outcomes. This kind of exploration gives scientists a broader perspective, as they can compare and contrast these alternate scenarios with our reality. One fascinating aspect of these simulations is their ability to illustrate the delicate balance of forces that govern our universe. For instance, if the strength of gravity were slightly different, the formation of stars, planets, and even life as we know it might never have occurred. By adjusting parameters within simulations, scientists can witness how small changes can create drastically different cosmic structures or even prevent the existence of galaxies entirely. This helps inform our understanding of why our universe is uniquely structured the way it is. Moreover, these simulations allow scientists to test various cosmological theories. For example, researchers can simulate the evolution of the universe from the Big Bang onward under different conditions. By tracking how galaxies cluster, how dark matter behaves, and how cosmic expansion proceeds in alternative scenarios, they can evaluate how well our current theories hold up against this data. This iterative process of modeling, comparison, and refinement is central to advancing our knowledge of the universe. Ultimately, simulations of alternate universes not only engage our imagination, but also serve as critical experiments that sharpen our understanding. They push the boundaries of what we know and inspire further inquiry into the fundamental workings of the cosmos. By examining these simulated realities, we gain insights that might reveal why our universe is uniquely suited for life, adding depth to our quest for knowledge about the cosmos that surrounds us. The holographic principle is a fascinating concept in modern astrophysics that reshapes our understanding of space, time, and information. At its core, this principle suggests that all the information contained within a three-dimensional space can be represented as a two-dimensional surface. This idea originated from theories in black hole physics, particularly proposed by scientists like Gerard T. Hooft and Leonard Susskind. They noticed that the amount of information that can be stored by a black hole is directly related to its surface area rather than its volume, leading to the emergence of this mind-bending principle. What makes the holographic principle particularly intriguing is its implications for the nature of reality itself. It challenges the traditional view of dimensions by proposing that our familiar three-dimensional world might actually be an elaborate projection of information encoded on a distant two-dimensional surface. This perspective encourages scientists to think about the universe in entirely new ways, prompting deeper investigations into the relationships between gravity, quantum mechanics, and the structure of space-time. In practical terms, this principle offers pathways to bridge the gaps between general relativity, which describes gravitation on cosmic scales, and quantum mechanics, the foundation governing the subatomic realm. The holographic principle could potentially offer insights into major unsolved puzzles in physics, such as understanding black holes and the very fabric of the universe itself. It has sparked renewed interest in string theory as well, where the idea of extra dimensions and supersymmetry intertwine with the holographic outlook. As researchers continue exploring this profound concept, the holographic principle stands as a testament to our deepening understanding of the cosmos. It urges us to reconsider not just what we know about black holes, but also the fundamental nature of space itself, leading to innovative and exhilarating possibilities about the universe and our place within it. Imagine a reality where every choice you make branches off into a different dimension, creating parallel lives in worlds that run alongside our own. These concepts of parallel dimensions challenge our understanding of what reality truly is. Rather than seeing our universe as a singular linear path, we are invited to envision a complex web of possibilities. This idea implies that every decision leads to a new branch in the cosmic tree of existence, opening up avenues we may never directly experience, but which theoretically coexist. At the heart of the idea of parallel dimensions is the multiverse theory, which suggests that our universe is just one of an infinite number of universes. Each universe might follow different physical laws or timelines, leading to variations of ourselves living out alternative realities. For example, in one dimension, you could be a scientist exploring the mysteries of black holes, while in another, you might have never pursued that path at all. This framework fascinates many because it enables a broader understanding of existence itself, pushing the boundaries of what we consider to be a singular reality. Moreover, understanding parallel dimensions could have profound implications in fields such as physics and cosmology. It challenges the traditional notions of time and space, suggesting that rather than being isolated events, all moments exist simultaneously in an interconnected tapestry. This could help explain certain phenomena in quantum physics, where particles behave unpredictably, seeming to exist in multiple states at once. Such concepts challenge our perceptions and may eventually lead to groundbreaking advancements in technology and our understanding of the universe. Ultimately, the idea of parallel dimensions invites us to rethink our place in the cosmos. It opens up a dialogue about destiny, choice, and the nature of existence. As we explore these dimensions more deeply, we may come to realize that the universe is far more intricate and mysterious than we ever imagined, revealing endless layers and possibilities waiting for us to discover. Recent advancements in technology have ushered in a new era for astrophysics, providing scientists with tools that enhance our understanding of the universe. One notable breakthrough is the development of highly sensitive telescopes, which can observe celestial phenomena in unprecedented detail. These state-of-the-art instruments, including both ground-based and space telescopes, allow researchers to detect light from the faintest corners of the universe. With capabilities like capturing occasions of gravitational lensing and observing distant galaxies, these technologies challenge existing theories and pave the way for new ones. Another significant advancement is in the realm of computational modeling and simulations. As technology improves, so does our ability to create intricate simulations of cosmic events, such as the formation of galaxies, black holes, and the behavior of dark matter. High-performance computers can process vast amounts of data and perform complex calculations more efficiently than ever before. This not only aids in visualizing theories, but also helps in predicting phenomena that have yet to be observed, giving rise to exciting new hypotheses. The utilization of artificial intelligence is also transforming astrophysics. Machine learning algorithms can sift through massive datasets collected from observing missions or simulations, identifying patterns that might elude human researchers. Recently, AI has proved invaluable in the search for exoplanets, where it analyzes light curves from distant stars to detect subtle changes that suggest the presence of orbiting planets, which could be crucial in the quest for extraterrestrial life. Finally, advancements in particle physics are helping to answer fundamental questions about the composition of the universe. Technologies such as particle accelerators and detectors are enabling scientists to explore dark matter and dark energy, two mysterious components that influence the universe's expansion and structure. As we unveil these technologies, they not only equip us with new ways to observe but also offer fresh perspectives on age-old mysteries, invigorating both theories and aspirations in the field of astrophysics. In the vast expanse of the universe, astronomers have discovered a remarkable array of exoplanets that challenge our understanding of what a planet can be. Among these celestial bodies, some stand out due to their bizarre characteristics. Take, for instance, the planet WASP 121b, which orbits a star located about 10 times closer than Earth is to our Sun. This world is classified as a hot Jupiter due to its massive size and proximity to its star, leading to temperatures that can exceed a scorching 1,600 degrees Celsius. What makes WASP 121b particularly unique is its atmosphere, which contains elements like magnesium and iron, creating a stunning spectacle akin to molten metal raining down. Then there's the peculiar LHS 3844b, which orbits a star about 45 light-years away from us. This planet is noteworthy because it has no atmosphere to speak of, resulting in extreme temperature fluctuations between day and night. Sunlit regions become blisteringly hot, while the dark side plunges into bone-chilling cold. The stark contrasts on this planet raise fascinating questions about its surface features, which may include dark basaltic rock formations forged by volcanic activity. Another fascinating example is HD 189733b, a planet that experiences storms of unimaginable ferocity. Winds on this exoplanet have been recorded at speeds exceeding 2,000 kilometers per hour, enough to turn raindrops into glass-like projectiles. The blue color of this planet, likely due to silicate particles in its atmosphere, adds to its enigma, making it visually enticing as well as terrifying. Lastly, we cannot overlook K2-141b, a world that has been described as the lava planet. This exoplanet literally has oceans of molten rock due to its extreme temperatures and proximity to its star. Unlike Earth, where water creates rivers, lakes, and oceans, K2-141b boasts flowing rivers of lava that reshape its landscape in real time. The dynamics of these unique exoplanets expand our comprehension of what might exist beyond our solar system and ignite our curiosity about the potential for life in such extreme environments. Identifying potentially habitable planets in distant solar systems is a complex process that combines advanced technology with our understanding of what makes a planet capable of supporting life. Scientists begin by focusing on what is known as the habitable zone. This is the region around a star where conditions might be just right for liquid water to exist on a planet's surface, one of the essential ingredients for life as we know it. The distance from the star, along with its size and temperature, helps determine this zone. Utilizing powerful telescopes, scientists search for exoplanets, which are planets outside our solar system. Instruments like the Kepler Space Telescope have significantly advanced this search by monitoring thousands of stars and detecting slight dips in their brightness. These dips occur when a planet passes in front of its host star, a method known as the transit method. By observing these transits, scientists can infer the size of the planet and its orbital period, helping to ascertain its potential location within the habitable zone. Once a planet is identified, scientists analyze its atmosphere and composition through spectroscopy. This technique allows them to study the light that passes through or reflects off the planet's atmosphere. By examining the chemical fingerprints left in this light, researchers can identify the presence of important elements and compounds, such as oxygen, carbon dioxide, and methane, which may indicate biological processes. Additionally, scientists also consider the planet's stability, which includes its climate and geological activity. A planet that maintains a stable temperature and has a magnetic field is more likely to have a conducive environment for life. Through these combined methods, researchers continue to expand our understanding of which distant worlds might harbor life, always exploring the vast possibilities that exist beyond our own solar system. Pluto, once revered as the 9th planet in our solar system, has gone through quite a journey since its discovery in 1930. Initially classified as a planet, its reclassification as a dwarf planet in 2006 by the International Astronomical Union stirred considerable debate. However, recent research has reignited interest in Pluto, particularly regarding its characteristics and classification. One of the remarkable discoveries came from the New Horizons mission, which flew by Pluto in 2015. This spacecraft provided stunning images and data revealing Pluto's complex geological features, including vast plains, icy mountains, and possible subsurface oceans. Such findings highlight that Pluto is not just a static, frozen body, but rather a dynamic world that may still experience geological activity. Another fascinating aspect relates to Pluto's atmosphere. Observations have shown that it has a thin yet significant atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. Researchers discovered that this atmosphere undergoes seasonal changes, expanding and contracting as Pluto moves closer to and further from the Sun along its elliptical orbit. These revelations suggest that Pluto is more akin to Earth in terms of environmental diversity than many initially thought. Despite these exciting discoveries, the debate over Pluto's classification remains unresolved. Some astronomers argue for a broader definition of what constitutes a planet, citing Pluto's fascinating features and complex environment as evidence of its planetary nature. As science evolves, so too does our understanding of the cosmos. Pluto's story is a reminder of the continuous quest for knowledge and the possibility that our definitions may change as we uncover more about our unique solar system. The atmosphere of Venus presents several intriguing anomalies that captivate scientists and astronomers alike. First and foremost, despite being the second planet from the Sun and having a surface temperature that can soar to around 900 degrees Fahrenheit, Venus's atmosphere is incredibly dense and composed mainly of carbon dioxide, with clouds of sulfuric acid. This combination creates an intense greenhouse effect, trapping heat and leading to a surface that is hotter than that of Mercury, despite its greater distance from the Sun. Another astonishing aspect of Venus's atmosphere is its superrotation. While the planet spins on its axis very slowly, taking about 243 Earth days to complete one rotation, the atmosphere behaves quite differently. The clouds at high altitudes travel around Venus in just about 4 Earth days, resulting in wind speeds that can exceed 150 miles per hour. This disparity raises questions about the mechanisms driving such fast-moving atmospheric currents, hinting at complex interactions between temperature, pressure, and atmospheric dynamics. Additionally, scientists have observed mysterious phenomena such as the presence of phosphine gas in small quantities. On Earth, phosphine is associated with life, as it is produced by certain microorganisms. While the detection of phosphine in Venus's harsh environment does not mean we have discovered life, it does challenge our understanding of the planet's chemistry. researchers are exploring possible non-biological processes that may contribute to phosphene's presence, adding another layer of complexity to our study of Venus. Finally, the exploration of Venus has revealed cloud formations and lightning activity akin to those seen in Earth's storms. Yet, the nature and origin of these storms remain a topic of research. Unlike Earth, where the water cycle drives atmospheric phenomena, Venus's storms could be influenced in part by sulfuric acid. These anomalies in Venus's atmosphere not only deepen our curiosity about our neighboring planet, but also serve as a stark reminder of the diversity of planetary environments within our own solar system. Rogue planets are fascinating celestial bodies that wander alone through the vastness of space, unbound by the gravitational influence of any star. Their characteristics set them apart in remarkable ways from planets that do have a star to call home. Rogue planets, often formed in the same way as conventional planets, may have been ejected from their original solar systems due to gravitational interactions or other cosmic events. As a result, they are typically much colder, often drifting through the universe without the warmth and light that comes from a nearby star. In terms of size, rogue planets can vary widely, ranging from small Earth-sized bodies to gas giants several times larger than Jupiter. However, without the energy provided by a star, their atmospheres can behave very differently. Some might harbor subsurface oceans warmed by internal geological processes, while others could be icy and barren, enveloped in thick atmospheric gases that barely contain heat. This leads to a diverse range of potential environments, some possibly even capable of supporting life in unexpected ways. Rogue planets also lack the regular seasonal cycles that planets orbiting stars experience, which can significantly impact their geological and atmospheric characteristics. Without a star's light, the climate on a rogue planet is largely static, resulting in potentially unchanging surface conditions over time. This might mean that instead of experiencing winters and summers, these planets inhabit a more constant environment, raising interesting questions about their potential for hosting ecosystems or sustaining heat. Ultimately, rogue planets add to the rich variety of worlds in our universe. Their solitary existence challenges our traditional views of planetary systems, reminding us that the cosmos is full of surprises. As we continue to study these elusive wanderers, we may uncover new aspects of planetary formation and evolution, revealing more about our universe and perhaps even the origins of life itself. Astronomers face numerous challenges when studying distant exoplanets, planets that orbit stars beyond our solar system. One of the primary difficulties is the immense distances involved. Many of these exoplanets are light years away, which means that the light we receive from them is a blend of faint signals drowned in the brilliance of their parent stars. Detecting such faint signals requires advanced technology and intricate techniques that can isolate and identify these remote worlds. One effective method used is the transit method, which involves monitoring the brightness of a star. If an exoplanet passes in front of its star from our perspective, it causes a temporary dimming of the star's light. By precisely measuring this dip in light, astronomers can infer the size of the planet and even gain insights into its atmosphere. However, this method relies on the planet's orbital alignment, making it a bit of a waiting game. Consequently, astronomers must observe many stars over extended periods to discover even one exoplanet. Another significant challenge is the atmospheric composition of these distant worlds. Determining what an exoplanet's atmosphere contains provides vital clues about its potential for supporting life. Astronomers overcome this by employing spectroscopy. This technique analyzes the star's light that filters through an exoplanet's atmosphere during a transit. Different gases absorb and emit light at specific wavelengths, allowing scientists to detect the presence of elements like water vapor or carbon dioxide, offering tantalizing hints about the planet's conditions. Advancements in technology, such as the development of space telescopes like the James Webb Space Telescope, are revolutionizing the study of exoplanets. These instruments are designed to observe in various wavelengths, making it easier to gather data on distant planets. Additionally, international collaborations and research institutions pooling their resources and expertise are vital in overcoming these challenges. Through innovation and teamwork, astronomers continue to push the boundaries of our understanding, gradually uncovering the countless secrets that distant exoplanets hold. The discovery and study of dwarf planets such as Eris and Haumea have significantly enriched our understanding of the solar system's complexity and diversity. For many years, Pluto was considered the largest known object in this category, but the identification of Eris and Haumea has prompted a re-evaluation of what defines a planet. Eris, for instance, is similar in size to Pluto, but has a mass that exceeds it, demonstrating that our solar neighborhood contains a variety of celestial bodies that challenge traditional classifications. In learning about these dwarf planets, scientists have explored their unique characteristics. Eris is particularly fascinating because it has a surface covered with a frost of methane ice, which suggests that it has geological activity and possibly even an atmosphere. Haumea, on the other hand, is known for its elongated shape and rapid rotation, which leads to interesting discussions about its formation and history. These discoveries highlight not only the variety among dwarf planets, but also the processes that shape these icy worlds in the Kuiper Belt. Studying these distant objects also helps researchers understand the early solar system. Eris and Haumea provide clues about the conditions and materials that existed during the formation of the planets. By examining their compositions and positions, scientists can infer details about planetary formation and migration. This insight can lead to better models for how our own Earth and other planets have evolved over billions of years, revealing an intricate story of the solar system's beginnings. Moreover, as we delve deeper into understanding dwarf planets, we confront the broader questions of how we categorize celestial bodies in the universe. The debate over the definition of a planet has led to ongoing discussions in both scientific and educational circles. This evolving perspective encourages a more inclusive viewpoint of the cosmos, making us rethink our place within it and appreciate the vast, intricate web of objects that populate our solar system. In the vastness of our solar system, some celestial bodies exhibit oddly peculiar orbital patterns that challenge our understanding of gravity and motion. For instance, the dwarf planet Haumea, residing in the Kuiper Belt, showcases a highly elongated orbit, unlike the more circular paths of many planets. This unusual pattern likely results from Haumea's rapid rotation, which causes a distinct shape, more elongated than round, like a rugby ball. Its interaction with the gravitational influences of other Kuiper Belt objects can also contribute to this intriguing behavior. Another notable example is the orbits of some distant objects like Sedna. Sedna has an elongated and tilted orbit that reaches far beyond what we typically observe. Theories suggest that gravitational perturbations, possibly from a yet undiscovered planet in the far reaches of our solar system, may be at play, drawing these celestial bodies into their strange trajectories. This hypothetical planet, sometimes dubbed Planet 9, could exert a gravitational influence on these distant wanderers, pulling them into such elongated orbits. The Oort cloud, a massive shell of icy bodies surrounding the solar system, also sparks curiosity. Some comets originating from this region follow highly elongated and irregular orbits that take them deep into the inner solar system. The gravitational forces from passing stars or galactic tides could disrupt their paths, sending them spiraling toward the sun in a stunning display of celestial dynamics. This interplay highlights the complex interactions in our galaxy, showcasing a dance of forces that dictate the behavior of these distant worlds. These strange orbital patterns remind us that our solar system is not as orderly as it seems. Each unusual trajectory tells a story about the dynamic forces at play, revealing the mysteries of space and inviting us to ponder what other fascinating phenomena might lie just beyond our current reach. As we continue to explore and understand these celestial wanderers, we further uncover the intricate tapestry of our universe. Recent discoveries about Mars have reignited interest in the quest for extraterrestrial life, prompting scientists to consider the planet as one of our closest potential neighbors for life beyond Earth. Mars has long fascinated researchers due to its similarities to our own planet, but advancements in exploration and technology have unveiled a more complex picture of its past and present. Evidence indicating that Mars once harbored liquid water, a crucial ingredient for life as we understand it, suggests that this dry, dusty world may have been much more hospitable than it is today. Explorations by rovers, such as Perseverance, have revealed signs of ancient riverbeds and lake deposits, bolstering the idea that microbial life could have flourished there billions of years ago. The discovery of organic molecules in Martian soil adds another layer of intrigue, as these are the building blocks of life. While organic molecules alone do not prove life existed, their presence indicates that the essential ingredients for life were available in Mars' past. As researchers continue to analyze these findings, they pose new questions about the potential for life to have arisen on Mars. Moreover, scientists are investigating the Martian atmosphere, where they have detected trace gases like methane, which can be produced by biological processes on Earth. This tantalizing clue raises the possibility that, even today, microbial life could exist beneath the Martian surface, where conditions might be more favorable. Such glimmers of hope encourage scientists to further explore the red planet and search for definitive signs of life, turning Mars into a vibrant focal point in the study of astrobiology. Through these recent discoveries, Mars has transformed into a new frontier in our understanding of life in the universe. Each mission yields fresh data, allowing us to piece together the planet's history and its potential to host life, past or present. As we continue to investigate this enigmatic neighbor, the journey not only enriches our comprehension of Mars, but also challenges our ideas about what life can be and where it might exist. The dream of answering the question of whether we are alone in the universe might just be one mission away. Asteroids and comets serve as cosmic time capsules, offering invaluable clues about the early solar system and the processes that led to the formation of our planets. When we look at these celestial bodies, we are essentially peering back into the primordial material that existed over 4 billion years ago. They are remnants from the chaotic period when our solar system was still forming, and studying them helps scientists piece together the story of how our planetary neighborhood came to be. Asteroids, primarily located in the asteroid belt between Mars and Jupiter, are rocky leftovers from the early solar system. They contain minerals that were formed in the initial stages of solar system development, providing insights into the conditions that prevailed at that time. Comets, on the other hand, are often found in the distant reaches of the solar system, typically in the Kuiper belt or the Oort cloud. Their icy compositions reveal how volatile compounds were distributed throughout the early solar system. By analyzing these bodies, we can better understand the building blocks of planets and the processes that shaped them. Moreover, the study of asteroids and comets helps us understand the potential for life. Comets, in particular, are thought to have delivered water and organic compounds to the early Earth, contributing to the conditions necessary for life to emerge. This connection prompts intriguing questions about the delivery of life's ingredients across the universe and whether similar processes could have occurred on exoplanets in distant solar systems. In recent years, various missions have targeted asteroids and comets for exploration. For example, NASA's mission to the asteroid Bennu aims to collect samples and return them to Earth for study. These missions enhance our understanding and continue to unveil the secrets these objects hold about our own planet's origins and the broader dynamics of planetary formation throughout the galaxy. Each new finding helps us craft a more complete picture of our cosmic beginnings. In the centers of many galaxies, astronomers have discovered intriguing phenomena, primarily concerning supermassive black holes. These colossal objects, which can be millions or even billions of times the mass of our Sun, are thought to reside at the heart of nearly every large galaxy. However, our understanding of their formation and the dynamics surrounding them remains partially veiled in mystery. Observations reveal that supermassive black holes often exert an intense gravitational influence on their surroundings. Stars and gas clouds can be caught in their grasp, rotating around them at incredible speeds, which would lead to significant energy emissions. Additionally, when matter spirals into these black holes, it creates an accretion disk that heats up dramatically, emitting X-rays and other forms of radiation. This phenomenon generates intense bursts of energy, making the centers of such galaxies some of the brightest objects in the universe. Yet despite this illumination, many questions linger about the formation and growth of these behemoths. Moreover, there are perplexing instances where supermassive black holes seem to be interacting in ways that challenge our current models of cosmic evolution. Some galaxies appear to host unexpectedly large black holes, far exceeding the anticipated sizes based on the amount of surrounding matter. This raises questions about whether these black holes formed through the merger of smaller ones, or if they could have grown rapidly through other mechanisms, such as the direct collapse of massive gas clouds in the early universe. Another fascinating aspect is the presence of relativistic jets, streams of charged particles ejected at nearly the speed of light from the poles of some supermassive black holes. These jets can extend vast distances into space and impact the host galaxy's evolution, yet how exactly they form is not fully understood. The interplay of these jets with surrounding matter hints at a complex relationship between black holes and their cosmic neighborhoods, suggesting that there is still so much to explore about the mysteries lying at the heart of galaxies. Galactic collisions are among the universe's most spectacular events, creating a cosmic ballet of gas, stars, and gravitational forces. When two galaxies collide, they don't slam into each other like solid objects. Instead, their immense clouds of gas and dust interact in a much softer manner. This interaction can trigger a surge of gravitational forces that compress these clouds, leading to regions of increased density. As gas gets compressed, it can collapse under its own gravity, giving birth to new stars. During these collisions, the gas and dust isn't evenly spread across the galaxies. As they merge, spiral arms can form and become highly active star-forming regions. Massive clouds can collapse and ignite nuclear fusion, creating young, bright stars. These new stars can shine brilliantly for millions of years, and as they age, they often explode as supernovae, further enriching the surrounding space with heavier elements. This process can lead to a sort of stellar renaissance in the aftermath of a collision, with new stars populating the cosmos. However, these galactic encounters are not without their quirks and anomalies. One such anomaly is the formation of tidal tails, elongated streams of stars and gas that trail off from the galaxies during the collision. These tidal forces can produce unusual shapes and structures that lead to further star formation in regions far removed from the initial collision point. Moreover, the gravitational chaos can result in some stars being flung into intergalactic space, while others may even be captured by the gravitational field of the newly formed galaxy. In addition to these fascinating phenomena, galactic collisions can also disrupt existing star systems. Some stars may lose their orbits, while others may merge, potentially giving rise to binary star systems or even black holes. These dynamic interactions weave a complex tapestry of cosmic evolution, showing us how the universe is constantly transforming and regenerating. The collision of galaxies is not just destruction, it's a vibrant catalyst for creation within the cosmos. The Great Attractor is a fascinating phenomenon that sheds light on the forces shaping our universe. It is a gravitational anomaly located in the direction of the Centaurus constellation, roughly 100 million light-years away from Earth. This colossal mass influences the motion of galaxies in our local supercluster, pulling them toward it with immense gravitational force. Imagine a giant cosmic spider with a web woven of galaxies, drawing them closer into its center. While the Great Attractor itself is not distinctly visible due to intervening galaxies and cosmic dust, its existence is inferred through the peculiar velocities of galaxies within its grasp. Galaxies aren't moving randomly, they exhibit a noticeable drift toward this gravitational well. This discovery pushed astronomers to rethink how galaxies interact and cluster together in the vastness of space. The significance of the Great Attractor extends beyond just its gravitational influence. Studying it enhances our understanding of the large-scale structure of the universe and the distribution of dark matter. It serves as a reminder that much of the universe remains hidden from direct observation, with invisible forces at play that govern the motions of celestial bodies. Moreover, the Great Attractor raises profound questions about the nature of the universe's expansion. As the universe expands, the influence of such gravitational structures provides insight into how gravity operates on a cosmic scale. By unraveling the mysteries of the Great Attractor, we unlock deeper truths about our universe, its composition, and the forces that bind it together. Each new revelation adds a layer to our understanding of the cosmic tapestry in which we exist. The rotation of galaxies plays a crucial role in shaping our understanding of dark matter. When astronomers observe galaxies, they often notice something peculiar. The outer regions of these galaxies rotate at speeds that seem unexplainable by the visible mass alone. According to the laws of physics, especially Newton's law of gravity, We would expect the outer stars to move more slowly, similar to how planets farther from the Sun take longer to orbit. However, this is not what observations reveal. Many galaxies, including our own Milky Way, exhibit a flat rotation curve. This means that the rotational speed of stars remains relatively constant, even at great distances from the galaxy's center. If we consider only the visible matter such as stars and gas, the expected rotational speeds should decline. This significant discrepancy suggests there must be additional unseen mass exerting gravitational influence, leading scientists to propose the existence of dark matter. Dark matter is thought to be a form of matter that does not emit, absorb, or reflect light, making it invisible and undetectable through traditional means. Instead, its presence is inferred through its gravitational effects on visible matter, particularly in how galaxies rotate. Models incorporating dark matter provide a more accurate depiction of a galaxy's mass distribution, resolving the paradox of the rotation curves. Instead, its presence is inferred through its gravitational effects on visible matter, particularly in how galaxies rotate. Models incorporating dark matter provide a more accurate depiction of a galaxy's mass distribution, resolving the paradox of the rotation curves. The idea of dark matter helps explain not only the motion of galaxies, but also larger cosmic structures, such as galaxy clusters and the overall formation of the universe. By studying the rotation of galaxies, astrophysicists gather essential clues about the nature of dark matter, a mysterious component that dominates the universe's mass-energy balance. This enigma continues to intrigue scientists, shaping the future of cosmological research and our quest to understand the cosmos. Stellar nurseries, often referred to as molecular clouds, are vast regions in space where new stars are born. These clouds are predominantly composed of gas and dust, primarily hydrogen, along with a mixture of other elements. Within these cool and dense regions, gravity plays a pivotal role in drawing the material together, forming clumps that can collapse over time. As these clumps condense, they can ignite nuclear fusion, giving birth to new stars. The entire process is a natural and beautiful cycle that contributes to the dynamic life of galaxies. What makes stellar nurseries particularly fascinating is their ability to create unexpected anomalies within galaxies. When a star forms, it tends to generate strong stellar winds and radiation, which can push surrounding material away, clearing out regions of the nursery. Alternatively, if a group of stars forms close together, their collective energy can lead to supernova explosions. These explosive events not only scatter heavier elements throughout space, but can also compress nearby gas and dust, triggering the formation of even more stars. This feedback mechanism often leads to irregular patterns of star formation, creating clusters or even chaotic regions within a galaxy. Moreover, some stellar nurseries can have surprisingly bright and distinctive appearances due to the energetic processes occurring inside them. For instance, the light generated by young stars can heat surrounding dust, causing it to emit radiation in the infrared spectrum. As a result, these glowing regions can sometimes be seen from great distances, revealing where new stars are actively coming to life. The contrasting shades of color that emerge can tell astronomers much about the age and dynamics of the star formation happening within those clouds. In this way, stellar nurseries are not just passive locations for star formation. They actively shape the structure and behavior of galaxies. The interplay of birth and death of stars and the accompanying anomalies illustrates the ever-evolving nature of the cosmos, reminding us that through chaos, beauty emerges in the vastness of space. This ongoing cosmic dance continues to captivate the imagination of scientists and stargazers alike, revealing the intricate tapestry of the universe we inhabit. The intriguing phenomenon of some galaxies appearing to be missing dark matter challenges our understanding of the universe. Observations show that while most galaxies are thought to contain substantial amounts of this elusive substance, a few seem to be lacking it entirely. This discrepancy raises crucial questions about the formation and evolution of galaxies over cosmic time. One of the key examples of this oddity can be found in dwarf galaxies, which are smaller and dimmer than their more massive counterparts. Some of these dwarf galaxies exhibit an unexpected distribution of visible matter and velocity patterns, suggesting that they do not contain the quantities of dark matter typically associated with their size. Researchers propose that these missing dark matter galaxies may have experienced different formation histories, perhaps due to interactions with larger galaxies or the influence of environmental factors in their cosmic neighborhoods. The implications of such findings stretch far beyond the missing material itself. Understanding these peculiar galaxies can shed light on the nature of dark matter, a mysterious substance that makes up a significant portion of the universe. By studying how these galaxies formed and how they behave, scientists can refine their models of dark matter's role in galaxy formation and structure. Moreover, these anomalies in dark matter distribution challenge existing theories, prompting astronomers to rethink the fundamental mechanics governing our universe. Each discovery brings us one step closer to unraveling the complexities of cosmic evolution, inviting us to explore the many mysteries that lie beyond our observable realm. When we look at the vast expanse of the universe, we find some truly staggering structures that stretch across unimaginable distances. The largest known structures include colossal formations like galaxy superclusters and massive filaments of galaxies, which form part of what is called the cosmic web. One of the most notable superclusters is the Hercules Corona Borealis Great Wall, which is so immense that it spans about 10 billion light-years across. These structures are not just random. They are intricately woven patterns of galaxies, gas, and dark matter, created by the gravitational pull within the universe. Understanding these colossal formations began with astronomers mapping galaxies and their distributions. Initially, early telescopes allowed for the identification of galaxies in clusters. However, it was through advanced technology, like the use of radio telescopes and space-based observatories, that scientists could detect fainter objects, leading to the discovery of larger cosmic structures. Optical surveys, such as the Sloan Digital Sky Survey, have been pivotal in revealing the large-scale structure of the universe over time. These observations have shown us that galaxies are not evenly spread out in space. Instead, they tend to be located along filaments and walls, with vast voids in between, a revelation that dramatically reshaped our understanding of the universe. Moreover, recent studies have leveraged techniques such as gravitational lensing, where the gravity of massive objects bends the light from distant galaxies. This innovative method not only allows scientists to observe distant galaxies, but also helps map the distribution of dark matter, which plays a critical role in the formation of these massive structures. Using both light and gravity, researchers discovered intricate webs of galaxies that confirm the cosmic web theory. As we continue to explore the universe, each new discovery adds to the picture of how our cosmos evolves. The study of these gigantic structures is far more than just a pursuit of the largest entities. It reveals the underlying processes that govern the formation of galaxies and the overall dynamics of the universe. Each of these vast formations tells us a story about the birth and evolution of galaxies, dark matter, and the universe itself, making our quest to understand them not just scientific but profoundly philosophical as well. Magnetic fields in galaxies are intriguing phenomena that influence a variety of celestial processes and help explain some of the anomalies we observe in the universe. These invisible fields, often extending across vast distances, arise from the motion of charged particles, such as electrons within galaxies. While we often think of magnets in familiar terms, like a refrigerator magnet, galactic magnetic fields operate on a much grander scale, shaping the behavior of cosmic dust, gas, and even star formation. One key area where magnetic fields play a significant role is in the dynamics of galaxy formation and evolution. These fields affect the motion of ionized gas, which constitutes a large part of a galaxy's mass. As charged particles spiral along magnetic field lines, they lose energy and influence gas density and temperature, which in turn can impact star formation rates. This coupling between magnetic fields and interstellar gas provides a deeper understanding of why some galaxies flourish with new stars while others remain dormant. Moreover, magnetic fields can help explain various anomalies observed in cosmic radiation, particularly in the behavior of cosmic rays. These high-energy particles can originate from stellar explosions or other energetic processes. However, their paths can be dramatically altered by the magnetic fields present in galaxies. This alteration can lead to unexpected results in observational data, including shifts in the intensity and distribution of cosmic rays we detect on Earth. thus creating a richer and more complex picture of the galaxy's environment. Finally, researchers are leveraging advanced observational tools and simulations to better understand these magnetic fields. As we continue to uncover the intricate tapestry of galactic dynamics, it becomes increasingly clear that magnetic fields are not mere background players. They are vital components that influence everything from the birth of stars to the distribution of cosmic rays, offering a key to unlocking the complex mysteries of our universe. The more we learn, the more these invisible forces intrigue and challenge our understanding of cosmic phenomena. Cosmic filaments play a pivotal role in the large-scale structure of the universe, acting as the grand highways of galactic formation and distribution. These immense threads, which can stretch hundreds of millions of light-years across, are composed primarily of galaxies, gas, and dark matter. They are part of a cosmic web that characterizes the universe, where dense regions filled with galaxies and clusters lie along these filaments, while vast voids exist in between. The formation of cosmic filaments is a fascinating result of gravitational forces. As the universe expanded from the Big Bang, matter began to clump together under gravity. Regions of higher density attracted more matter, eventually leading to the formation of these elongated structures. This gathering of matter not only shapes the distribution of galaxies, but also influences the characteristics of the cosmic environment. Within these filaments, galaxies are more likely to interact, merge, and grow, shaping the evolution of structures we see today. Additionally, cosmic filaments are thought to play a crucial role in the flow of gas and dark matter throughout the universe. They act as conduits, funneling gas into the centers of galaxy clusters, which can ignite star formation and enhance the growth of galaxies. This inflow of material can trigger various cosmic events, leading to the creation of new stars and the recycling of materials back into the cosmic ecosystem. Understanding cosmic filaments enriches our comprehension of the universe's architecture. Their significance lies not just in their physical presence, but in how they guide the evolution of galaxies and influence the cosmic dynamics. Exploring these structures illuminates the complex interplay of forces that has shaped our universe over billions of years, making them a fundamental topic of interest in cosmology. Supernovae are among the most explosive events in the universe, marking the death of certain massive stars and releasing an immense amount of energy in a fleeting moment. When these stellar giants explode, they don't just vanish. Their mighty blast sends shockwaves rippling through their host galaxies and beyond. This cataclysmic event can trigger a chain reaction that impacts countless neighboring structures in both visible and subtle ways. One significant effect of a supernova is its ability to create new star formation in the surrounding regions. The force of the explosion compresses nearby gas and dust, triggering the gravitational collapse necessary for new stars to ignite. This phenomenon can lead to the birth of new stellar populations, enriching the galaxy with fresh, luminous stars. Over time, these newborn stars contribute to the galaxy's evolution, altering its appearance and structure. Additionally, supernovae play a crucial role in dispersing heavy elements into the interstellar medium. These elements, forged in the heart of dying stars, are released into space when a star explodes. This process enriches the surrounding gas clouds with materials necessary for the formation of planets, life, and other cosmic structures. Thus, each supernova acts as a cosmic recycling center, ensuring that the elements essential for life are continually reintroduced into the universe. Moreover, the remnants of supernovae can influence the dynamics of their host galaxies. The supernova blast can modify the motions of nearby stars and gas, leading to shifts in their orbits. Over time, multiple supernovae can collectively reshape regions of a galaxy, contributing to galactic winds and other phenomena that drive the evolution of galaxies over cosmic timescales. The life and death of stars shape the universe in ways more profound than we often realize, demonstrating the intricate connections between birth, death, and rebirth in the cosmos. Early astronomers played a pivotal role in shaping our understanding of celestial anomalies, laying the groundwork for modern astrophysics. Long before the advent of telescopes, these ancient observers diligently noted the patterns of the night sky, meticulously charting the movements of stars and planets. They recognized irregularities in celestial motions that didn't conform to the predictable paths of the heavens, questioning why some heavenly bodies appeared to wander against the backdrop of the lifelong stars. These anomalies often sparked profound curiosity and speculation, which ultimately led to significant advancements. For instance, the ancient Greeks, with philosophers like Ptolemy and Aristotle, sought to explain retrograde motion, the peculiar behavior of planets that sometimes appeared to move backward in their paths. The geocentric model proposed by Ptolemy suggested that the Earth sat at the center of the universe, with celestial bodies orbiting around it. This intricate system employed epicycles to account for these anomalies. Even though this view was later proven inaccurate, it displayed early attempts to embrace complexity and encouraged further observation and refinement of astronomical models. As telescopes emerged in the 17th century, figures like Galileo Galilei revolutionized astronomy. He observed spots on the Sun, moons around Jupiter, and the phases of Venus, reinforcing the heliocentric theory proposed by Copernicus, which positioned the Sun at the center of our solar system. Galileo's discoveries demonstrated that celestial anomalies were not mere imperfections, but rather integral parts of a much larger cosmic ballet, shifting our understanding and inspiring subsequent astronomers. The quest for understanding celestial anomalies didn't stop at our solar system. As more advanced telescopes and instruments were developed, astronomers began exploring distant galaxies, discovering phenomena like supernova, black holes, and cosmic microwave background radiation. Each of these anomalies provided crucial insights into the nature of our universe, enriching our understanding of its origins and evolution and revealing the extraordinary complexities hidden within the cosmos. Early astronomers set the stage for this journey, reminding us that each anomaly is not just a puzzle to solve, but a door to deeper understanding. Albert Einstein's theories, particularly his theory of relativity, revolutionized our understanding of the universe in profound ways. Before his work, the scientific community largely viewed space and time as fixed and unchanging. However, Einstein introduced the concept that both space and time are interconnected in a single continuum known as spacetime. This insight shifted the foundations of physics, revealing that massive objects like stars and planets can warp this fabric, influencing the motion of other objects. This was a radical departure from Newtonian physics, which had dominated for centuries. Einstein's general theory of relativity, published in 1916, suggested that gravity is not merely a force acting at a distance, but rather a curvature in space-time caused by mass. This understanding allowed scientists to better explain various cosmic phenomena, including the orbits of planets, the bending of light around massive objects, and the expansion of the universe itself. The famous observations of light from distant stars bending during solar eclipses provided early experimental support for his theories and stirred excitement in the scientific community. Even more astonishing was the realization that general relativity laid the groundwork for modern cosmology. It allowed theorists to develop models of the universe that included concepts such as black holes, cosmic inflation, and the Big Bang. Before Einstein, the universe was often perceived as static and eternal. His work opened the door to understanding a dynamic and evolving universe, leading to discoveries that have shaped contemporary astrophysics. Today, Einstein's theories continue to guide research in cosmology and astronomy. They inform our exploration of dark energy and dark matter, elements that dominate the universe yet remain largely mysterious. Einstein's legacy, then, is not just the introduction of bold ideas. It is a profound transformation of how we perceive our place in the cosmos and the laws that govern reality. His theories inspire continued inquiry into the extraordinary universe, encouraging us to explore further and ask deeper questions about the nature of existence. Throughout history, women have made significant contributions to astrophysics, often overcoming substantial barriers to leave their mark on the field. One of the most notable figures is Henrietta Leavitt, who worked at Harvard in the early 20th century. Leavitt studied variable stars called Cepheids, discovering a relationship between their brightness and their periodicity. This groundbreaking work established a critical method for measuring cosmic distances, allowing astronomers to unlock the scale of the universe and expand our understanding of its vastness. Another remarkable woman in astrophysics is Vera Rubin, whose research in the mid-20th century provided compelling evidence for dark matter. By observing the rotation curves of spiral galaxies, Rubin revealed that the outer regions of these galaxies rotate much faster than expected. This observation defied traditional physics and implied the presence of unseen mass, dark matter, that exerts gravitational influence. Her work significantly advanced our understanding of the universe's composition and prompted further research into the enigmatic nature of dark matter. Additionally, we cannot overlook the contributions of Jocelyn Bell Burnell. As a graduate student in the 1960s, she discovered the first pulsar, a highly magnetized rotating neutron star that emits beams of electromagnetic radiation. This discovery not only enriched our understanding of stellar evolution, but also ignited a new field of study within astrophysics. Although she initially received limited recognition for this monumental finding, the pulsar opened doors to many crucial insights about the universe, demonstrating how one individual's discovery can ripple through science. The impact of these women's contributions extends beyond their individual achievements. Their work has empowered future generations of researchers, emphasizing the importance of diversity in science. Today, women in astrophysics continue to lead groundbreaking research and inspire others to explore the cosmos, ensuring that their legacy will resonate for ages to come. Their discoveries challenge us to look deeper into the universe and remind us that the mysteries of space are best understood when a variety of voices contribute to the conversation. The invention of the telescope marked a turning point in our understanding of the universe, opening a window onto the cosmos that humanity had never before experienced. Prior to the telescope, our view was limited to the naked eye, and our grasp of the heavens relied heavily on observation from Earth. With the arrival of telescopes in the early 17th century, we began to perceive celestial bodies not merely as points of light, but as complex and dynamic objects. One of the earliest advocates of the telescope was Galileo Galilei. Using his handmade telescope, he observed the moons of Jupiter, which revealed that not all celestial bodies orbited Earth. This was a critical observation that challenged the long-held belief in a geocentric universe, where Earth was considered the center of all things. Galileo's discoveries laid the groundwork for a new understanding of our place in the universe, showing that it was far more complex than previously thought. As telescopes improved through the centuries, so did our knowledge of the vastness of space. The intricate details of planets, the structure of galaxies, and the behavior of distant stars became clearer. The shining rings of Saturn, the craters on the Moon, and the swirling arms of spiral galaxies were all unveiled through advancements in telescope technology. Each new iteration brought more power, revealing phenomena such as nebulae and supernovae, which significantly expanded our understanding of stellar life cycles. With these advancements, astronomers began to formulate deeper questions about the nature of the universe. Telescopes paved the way for the study of dark matter, dark energy, and the very fabric of space-time. Today, powerful observatories like the Hubble Space Telescope allow us to peer billions of light-years away into the depths of space, fundamentally altering how we comprehend the cosmos. Telescopes continue to be indispensable tools, inviting us to explore and appreciate the mysteries of the universe in ways that were once unimaginable. Carl Sagan was a remarkable figure in the world of science, renowned for his ability to communicate complex ideas in a way that captivated the public's imagination. One of his most significant contributions was popularizing the concept of space anomalies, from black holes and quasars to the peculiarities of distant celestial bodies. Through his television series, Cosmos, which first aired in 1980, Sagan introduced audiences to these fascinating phenomena using a blend of stunning visuals and accessible language. He created a sense of wonder about the universe that resonated with viewers, making them curious about the mysteries beyond Earth. Sagan employed vivid storytelling to make science relatable. He often used metaphors and analogies drawn from everyday life, transforming abstract concepts into tangible ideas. For instance, he compared the behavior of light around black holes to water spiraling down a drain, allowing listeners to visualize a concept that might otherwise seem incomprehensible. This approach not only educated, but also inspired a generation to think more deeply about the cosmos and our place within it. Another avenue through which Sagan popularized space anomalies was through his writing. His books, such as Pale Blue Dot and Contact, combined scientific education with philosophical inquiry, urging readers to ponder both the enormity of the universe and the fragility of human existence. By marrying narrative with science, Sagan struck a chord with readers, encouraging them to consider how these anomalies fit into a larger cosmic story. His ability to connect emotionally with his audience was as important as the facts he presented. Ultimately, Carl Sagan's legacy endures through the curiosity he ignited in countless individuals. He not only explained scientific concepts, but also instilled a sense of wonder and urgency about exploring the unknown. By making space anomalies a topic of fascination for the general public, he helped to foster a culture of scientific inquiry that continues to thrive today. Thanks to his efforts, many people now view the study of the universe not just as an academic pursuit, but as a profound journey into the depths of existence itself. The space race, a pivotal era spanning from the late 1950s to the early 1970s, profoundly influenced our understanding of space anomalies. This rivalry, primarily between the United States and the Soviet Union, was driven by the desire to achieve monumental milestones in space exploration, leading both nations to invest heavily in technology and research. The focus on beating each other to various space milestones spurred unprecedented innovations and discoveries, particularly regarding the mysteries of our universe. During this intense competition, resources were poured into satellite technology, which provided scientists with the tools necessary to observe and study celestial phenomena in ways that were previously unimaginable. For instance, after the launch of the first artificial satellite, Sputnik, in 1957, scientists gained new insights into cosmic radiation and the Earth's magnetosphere. Moreover, the development of advanced telescopes, like the Hubble Space Telescope, allowed us to notably enhance the observation of space anomalies such as black holes and pulsars. The heightened emphasis on exploration also fostered international collaborations, especially as the limitations of nation-specific resources became apparent. Projects like the International Space Station included scientists and engineers from around the globe, sharing knowledge and techniques that accelerated discoveries related to dark matter and cosmic background radiation. These insights have provided critical context for understanding the broader workings of the universe and the complex nature of space anomalies. The space race ignited a newfound urgency in astronomical research, as both superpowers sought to outdo one another in their quest for knowledge. They laid the groundwork for countless advancements that have enriched our understanding of space, allowing us to unravel the mysteries of the cosmos and appreciate the anomalies that challenge our perceptions of reality today. Ancient civilizations made remarkable contributions to our understanding of the stars, often driven by their daily needs, spiritual beliefs, and the desire to navigate their world. Civilizations like the Babylonians, Egyptians, Mayans, and Greeks meticulously observed celestial patterns, leading to the development of early astronomy. Their work contributed significantly to future astronomical models, providing a basis for Greek and later Western astronomy. Meanwhile, the Egyptians linked their understanding of the stars with their mythology and architecture, aligning their pyramids with stellar constellations. They worshipped specific stars, believing them to be connected to their gods. For example, they associated the star Sirius with the annual flooding of the Nile, crucial for their agriculture. Their sophisticated solar calendar, built on a solar year of 365 days, showcased their exceptional attention to astronomical phenomena. The Mayans also excelled in astronomy, developing a calendar system that intricately combines celestial observations with their spiritual beliefs. They noted the appearance of the planet Venus and its connection to warfare and agriculture, allowing them to schedule significant events. Through their precise observations of celestial bodies, ancient civilizations not only enhanced their own understanding of the universe, but also forged a pathway that continues to shape modern astronomy. Their contributions remain a testament to human curiosity and our enduring quest to comprehend the cosmos. Throughout the history of space exploration, several missions have significantly expanded our understanding of distant planets, each revealing new secrets about our solar system and beyond. One of the most notable among them is NASA's Voyager program. Launched in the late 70s, Voyager 1 and Voyager 2 conducted flybys of Jupiter, Saturn, Uranus, and Neptune, sending back stunning images and invaluable data. The information gathered about the atmospheres, magnetic fields, and moons of these gas giants reshaped our understanding and sparked interest in the complex dynamic systems present in outer space. Another game-changing mission was the Galileo spacecraft, which was dedicated to studying Jupiter and its many moons. Launched in the late 80s, Galileo provided a wealth of information about not only the massive planet itself, but also its intriguing moons like Europa, which is believed to harbor a subsurface ocean. Such discoveries have opened up discussions about the potential for life beyond Earth, as Europa might have conditions suitable for supporting life as we know it. Close on the heels of these pioneering missions, NASA's Mars rovers, particularly Spirit, Opportunity, and Curiosity, have completely transformed our views on the red planet. With the ability to conduct on-site analyses and observations, these rovers have provided critical evidence about Mars's past geological processes and possible water presence. Curiosity's discovery of organic molecules hints at the planet's potential for ancient life, making these missions crucial tools in our quest to understand our neighboring planet. And let's not forget the more recent Juno mission, which has been orbiting Jupiter since 2016. Juno's advanced instruments are mapping Jupiter's gravitational and magnetic fields, revealing the structure of its atmosphere and investigating its complex weather patterns. Each of these missions contributes to a skyward puzzle, providing pieces that not only enlighten us about distant worlds, but also about our own planet and its place in the cosmos. With each mission, we push the boundaries of our knowledge further, sparking curiosity and wonder about the universe we inhabit. Developments in quantum mechanics have had a profound impact on the field of astrophysics, dramatically altering our understanding of the universe. At its core, quantum mechanics reveals that particles behave both like particles and waves, introducing a level of complexity and unpredictability that classical physics could not explain. This duality has implications for the very fabric of the cosmos, influencing theories on everything from the birth of stars to the behavior of black holes. One of the most significant ways quantum mechanics has influenced astrophysics is through the study of stellar evolution. Stars generate energy and heat through nuclear fusion, which relies on quantum tunneling, a phenomenon where particles can move through barriers they seem unable to cross. This process enables hydrogen nuclei to fuse into helium at temperatures lower than classical physics would suggest, altering our understanding of how stars maintain their life cycles. As a result, scientists have refined models of stellar formation and evolution, yielding deeper insights into how elements are created in the cosmos. Additionally, quantum mechanics plays a crucial role in understanding phenomena like neutron stars and the behavior of matter in extreme conditions. In these dense environments, the principles governing quantum particles become dominant, allowing astrophysicists to explore exotic states of matter. Research in these areas has led to revelations about how gravity and quantum mechanics interact, creating a bridge between two foundational pillars of modern physics. This interaction is key to developing a comprehensive understanding of the universe. Moreover, quantum mechanics also paves the way for modern technologies that enhance astrophysical research. Techniques such as quantum imaging and quantum computing begin to pave the path for more advanced simulations and observations of cosmic phenomena, enabling scientists to delve into realms previously thought elusive. By integrating these quantum principles into astrophysical studies, researchers continue to unravel the mysteries of the universe, blending the microscopic and the cosmic in an elegant dance of science. The Hubble Space Telescope, launched in 1990, has reshaped our understanding of the universe in profound ways. One of its most pivotal discoveries has been the measurement of the rate of expansion of the universe. Through observations of distant supernovae, scientists calculated that the universe is not only expanding, but the speed of that expansion is accelerating. This surprising finding led to the concept of dark energy, an enigmatic force that seems to permeate space, counteracting the attractive force of gravity on cosmic scales. Hubble has also provided invaluable insights into the formation and evolution of galaxies. Its stunning images of various galactic structures have revealed a rich diversity of shapes and sizes, from spiral galaxies like our Milky Way to peculiar and irregular forms. By examining the distribution and composition of stars within these galaxies, Hubble has deepened our understanding of how galaxies collide, merge, and grow over time, a process critical to the cosmic landscape. Moreover, the telescope has played a crucial role in studying exoplanets or planets outside our solar system. Hubble's observations have contributed to the detection of many of these distant worlds and have aided in examining their atmospheres. These findings have expanded our knowledge of potentially habitable zones within different star systems and have raised intriguing questions about the possibility of life elsewhere in the universe. Finally, Hubble has captured breathtaking images of distant celestial phenomena, such as nebulae and black holes. These observations not only inspire awe, but also reveal the intricate processes that shape our universe. Each discovery adds another layer to our cosmic story, reminding us of the vastness and complexity of the cosmos and sparking curiosity for what lies beyond our sight. Exploration of the outer solar system is a fascinating frontier for scientists, with several key missions poised to deepen our understanding of this distant region. One of the most anticipated missions is NASA's Europa Clipper, scheduled for launch in the year 2024. This spacecraft will focus on Jupiter's icy moon, Europa, which is believed to harbor a subsurface ocean beneath its frozen crust. Scientists are particularly interested in Europa because, with its potential for liquid water and chemical ingredients, it could be an environment suitable for life. The Clipper will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, analyzing its composition and the potential for habitability. Another noteworthy mission is the European Space Agency's JUICE, short for Jupiter Icy Moons Explorer. Slated for launch in 2023, JUICE aims to study not only Europa, but also Jupiter's other notable moons, Ganymede and Callisto. Ganymede is especially intriguing as it is the only moon in the solar system known to have a magnetic field of its own. The mission will look into the icy crusts of these moons and investigate their potential oceans, hoping to uncover more about their inner structures and the conditions that might support life. Furthermore, NASA's Dragonfly mission is making headlines for its innovative approach to exploring Titan, Saturn's largest moon. Set to launch in 2027, this unique rotorcraft will fly to multiple locations on Titan, examining its dense atmosphere and surface, which is covered in rivers and lakes of liquid methane and ethane. Dragonfly's goal is to understand the moon's prebiotic chemistry and assess its potential for life, making it one of the most ambitious missions to study extraterrestrial bodies. Additionally, there are ongoing discussions and proposals for future missions like a potential return to Uranus and Neptune, the ice giants of our solar system. These missions could include orbiters or landers designed to unveil the mysteries surrounding their atmospheres, magnetic fields, and unique weather phenomena. With each mission, we move closer to answering the profound questions about the origins of our solar system and the potential for life beyond Earth, illuminating the dark regions of our celestial neighborhood. Advancements in artificial intelligence are revolutionizing our approach to exploring the cosmos. Traditionally, astronomers would sift through vast amounts of data manually, looking for patterns or anomalies that could lead to groundbreaking discoveries. However, as the universe is filled with an overwhelming quantity of information, such as images from telescopes and various signal data from space, AI can analyze this data at an unprecedented speed and accuracy. Machine learning algorithms can be trained to recognize peculiarities in cosmic data that the human eye might easily overlook. For example, they can identify unusual patterns in the light curves of distant stars that may indicate the presence of exoplanets or even new types of celestial phenomena. This capability not only accelerates the discovery process, but also broadens the scope of what researchers can find. AI can flag anomalies that are entirely new to our understanding, pushing the boundaries of current scientific knowledge. Another amazing aspect of AI in this context is its potential to manage and interpret data from various sources simultaneously. Large-scale projects like the ongoing survey of the night sky by the Vera C. Rubin Observatory generate petabytes of data. AI can help classify this information in real time, aiding astronomers in finding transient events such as supernovae or gravitational waves. By efficiently processing these signals, AI can enhance our understanding of cosmic events that happen on timescales too quick for traditional human analysis. As we continue to seek answers about the universe, AI's role in enhancing our capabilities is undeniable. This technological evolution allows not only for faster discoveries, but also for deeper explorations into the mysteries of our cosmos. Thus, as we harness AI's potential, we move one step closer to unveiling the profound enigmas that lie beyond our planet. The construction of new observatories is vital in our ongoing quest to unravel the mysteries of the cosmos. As technology evolves, so do our capabilities to observe celestial phenomena that were once hidden from our view. Each new observatory acts like a powerful eye peering into the vast expanses of space, enabling scientists to collect data about stars, galaxies, and even the elusive dark matter that makes up much of the universe's mass. One of the primary benefits of building new observatories is advancements in observational technology. These facilities often include cutting-edge instruments that can detect wavelengths of light beyond what older telescopes could manage. For instance, while many telescopes primarily observe visible light, new ones explore infrared, ultraviolet, and even radio waves, revealing structures and processes in the universe we have yet to fully comprehend. This broadens our understanding of cosmic events such as the birth of stars, the life cycles of galaxies, and the mysterious energy that drives the universe's expansion. In addition to enhancing our observational reach, new observatories are strategically placed in locations with optimal conditions for astronomy. Many are constructed atop remote mountains or in desert regions, where the air is clear and dark skies prevail. This ensures minimal interference from atmospheric conditions or light pollution. These ideal settings allow astronomers to capture clearer images and more precise data, thus unlocking deeper insights into the fabric of the universe. Moreover, each new observatory serves as a center for collaboration, drawing scientists from around the globe. The pooling of diverse expertise and perspectives leads to innovative ideas and breakthroughs that propel our understanding forward. Through shared observations and discoveries, these scientific communities unite in a common goal: to confront the unanswered questions of our universe, all while igniting a sense of wonder and expanding humanity's knowledge of our cosmic home. Space tourism is more than just a thrilling adventure. It has the potential to significantly enhance our exploration and study of celestial bodies. First, commercial space flights allow a wider range of people to experience space travel. As more private companies enter the arena, we will see a diverse group of travelers. This democratization of space could bring fresh perspectives and innovative ideas about space exploration, leading to groundbreaking research and discoveries. Furthermore, space tourism activities can stimulate technological advancements. Developing spacecraft capable of carrying tourists requires cutting-edge technology, which in turn enhances equipment that could be used in scientific missions. Commercial ventures are incentivized to create more efficient propulsion systems, life support technologies, and safe landing mechanisms. These innovations can later be adapted for scientific exploration, making trips to celestial bodies more feasible and efficient. Moreover, increased public engagement in space tourism can generate greater interest and funding for scientific missions. As more people become captivated by the idea of visiting space, the demand for knowledge about our universe will rise. This heightened interest can encourage governments and private entities to invest in missions to the Moon, Mars, and beyond, enhancing our understanding of these distant worlds and their potential for human habitation. Ultimately, space tourism fosters a new era of collaboration between private enterprises and scientific institutions. Partnerships could emerge where resources, knowledge, and technology are shared, creating a holistic approach to space exploration. With each launch, not only does the allure of space grow for everyday people, but we also pave the way for deeper understanding and discovery of the celestial bodies that populate our universe. As humanity gazes at the stars, the dream of interstellar travel captures our imagination more than ever. Several remarkable technological innovations are emerging, steadily transforming this dream into a potential reality. One of the most talked about concepts is the use of light sails propelled by powerful lasers. By harnessing the light from these lasers, a small spacecraft could gradually accelerate, reaching speeds that bring the nearest stars within reach over time. Another intriguing development lies in the realm of nuclear propulsion. Researchers are exploring nuclear fusion, the same process that powers our sun, to produce energy for spacecraft. Theoretically, A fusion-powered vessel could generate immense thrust, allowing for faster travel to distant worlds. Innovative designs like the concept of a fusion rocket could provide a breakthrough in speed and efficiency, shrinking the decades of travel time that current propulsion methods would require. Also capturing attention is the idea of antimatter propulsion. Antimatter is the mirror image of matter, and when the two collide, they annihilate each other in a burst of energy greater than any chemical reaction. Although producing and storing antimatter are extremely challenging, its potential use in propulsion could revolutionize the way we think about space travel, making near-light-speed journeys viable. Finally, we cannot overlook the role of advanced robotics and artificial intelligence in future interstellar missions. These technologies will be crucial for navigating the vast unknowns of space, conducting scientific research, and even making decisions light years away from Earth. As we continue to explore and develop these innovations, the dream of reaching other star systems may evolve from science fiction to science reality. The future of telescopes holds exciting promise for expanding our understanding of exoplanets. These advanced instruments will provide unprecedented details about distant worlds beyond our solar system. Equipped with cutting-edge technology, they'll enable astronomers to explore the atmospheres of these planets in remarkable ways. By analyzing light that filters through an exoplanet's atmosphere during transits, scientists can decipher the composition, presence of chemicals, and even hints of potential habitability. One of the most significant advancements will be the ability to detect signs of life, or biomarkers, on distant exoplanets. Future telescopes will be adept at spotting gases like oxygen, methane, and carbon dioxide, which could suggest biological processes. The prospects of identifying these gases will deepen our exploration of what conditions are necessary for life as we understand it. It sparks the intriguing question of whether we share the universe with other living organisms, or if we are, as far as we know, uniquely alone. Another transformative aspect of these new instruments will be their capability to image exoplanets directly. Current telescopes often struggle to distinguish these distant planets from the bright glare of their parent stars. However, improved techniques such as coronagraphy and interferometry will allow astronomers to capture actual images of exoplanets. This visual evidence will help researchers study the surface and atmospheric conditions more closely, ultimately leading to new insights about their diversity and characteristics. As we continue to refine these technologies, our perspective on the cosmos could change dramatically. The thrill of discovery awaits us with each advancement, and the likelihood of uncovering new exoplanets, some potentially resembling Earth, fuels our curiosity. Each new telescope could bring us closer to answering fundamental questions about our place in the universe and whether there might be other life forms out there, creating a profound impact on our view of existence itself. International collaborations in space exploration have been pivotal in pushing the boundaries of our understanding of the universe. By pooling resources, knowledge, and talent from different countries, scientists and engineers can tackle challenges that may be insurmountable for individual nations. This collective effort brings together diverse perspectives and specialties, fostering innovative approaches to complex problems. For example, the partnership behind the International Space Station is a prime showcase of how collaboration can yield significant scientific advancements. One remarkable advantage of these alliances is the sharing of costs and expertise. Space missions are incredibly expensive and technically demanding. When multiple countries collaborate, they can share the financial burden, making ambitious projects more feasible. Countries that may have limited technological capabilities can benefit by accessing advanced technologies and knowledge from their partners. This exchange not only accelerates progress, but often results in breakthroughs that would not have been possible otherwise. Moreover, these collaborations cultivate a rich environment for scientific inquiry. When researchers from different cultures and regions unite, they can approach problems from unique angles. This variation can lead to novel hypotheses and experimental designs, further enhancing the research output. For instance, the joint efforts in Mars exploration have produced findings that deepen our understanding of the planet, including the evidence for water once being present on its surface, which has implications for the potential for life beyond Earth. Additionally, international partnerships in space exploration promote peaceful relations and global unity. Shared goals in the pursuit of knowledge can transcend borders and foster a sense of global community. Events such as the Hubble Space Telescope's discoveries have not only broadened our understanding of the cosmos, but have also brought together scientists from across the globe, demonstrating how cooperation in science can inspire humanity to look beyond differences. These collaborations are not just about sending spacecraft into the void. They represent a collective human drive to explore, learn, and understand the universe we inhabit. The moons of Jupiter and Saturn hold immense potential for scientific discoveries, primarily because they are diverse and intriguing worlds that may harbor conditions suitable for life. One of the most exciting prospects stems from Europa, one of Jupiter's largest moons. Beneath its icy crust lies a vast ocean of liquid water, which is essential for life as we know it. By studying Europa, scientists hope to uncover signs of microbial life, as well as learn more about the moon's geology and the chemical processes occurring beneath its surface. Similarly, Saturn's moon Enceladus has captured attention because of its impressive geysers that spew water vapor and organic molecules into space. These plumes suggest that there is also a subsurface ocean beneath its icy exterior. Analyzing samples from these geysers could provide clues about the moon's potential habitability. The discovery of life or even life's building blocks on these moons would fundamentally change our understanding of life in the universe and its resilience under extreme conditions. Additionally, the variety of other moons in these two planetary systems presents a unique tapestry for exploration. Moons like Ganymede, the largest moon in the solar system, possess magnetic fields and a substantial atmosphere, while Titan, Saturn's largest moon, features lakes of liquid methane. Each of these moons offers unique environments that may lead to groundbreaking discoveries related to planetary formation, atmospheric conditions, and the potential for life. The investigation of Jupiter and Saturn's moons may not only enrich our knowledge of these celestial bodies themselves, but could also shed light on the broader questions of life, habitability, and the mechanisms that govern the cosmic environment. Each mission that probes their secrets serves as a stepping stone toward understanding our place in the universe. The concept of time travel, while still grounded in theory, sparks a multitude of fascinating implications for the study of cosmic anomalies. Imagine being able to venture back to events like the formation of the universe or the birth of stars. Observing these monumental moments firsthand could provide insights into how these anomalies, such as black holes or supernova remnants, have evolved over time. In a theoretical framework, time travel could allow scientists to gather exhaustive data from moments lost to history. This could include understanding cosmic events like the collisions of galaxies or the behavior of dark matter in different epochs. By witnessing these phenomena as they unfold, researchers would be able to refine their models and theories, potentially unraveling some of the most perplexing mysteries of the cosmos. Additionally, time travel could provide a unique perspective on the origins of cosmic anomalies. For example, if we could travel back in time to study the early universe, we might encounter primordial black holes or the formation of the first stars. This would enable us to connect dots between observed anomalies and their theoretical origins, enriching our understanding of the universe's overall evolution. However, all of this remains firmly in the realm of speculation. Time travel introduces paradoxes and complexities that challenge our understanding of physics as we know it. Yet, contemplating the possibilities can ignite curiosity and open new avenues of thought in cosmology, inviting us to consider how the mysteries of time and space might intertwine in ways we have yet to discover. As humanity stands on the brink of exploring other planets, particularly Mars, ethical considerations regarding colonization come to the forefront. One of the most pressing issues is the potential disruption of any existing ecosystems. If we were to colonize a planet, we could inadvertently harm any microbial life or unique environments, much like how early explorers impacted the indigenous populations and ecosystems of Earth. This raises the question of our responsibility to protect alien life, even if it appears simple or primitive. Another consideration is the right to claim and inhabit other worlds. Can one nation or group lay claim to celestial bodies? The Outer Space Treaty of 1967 is a guiding framework, emphasizing that space exploration should benefit all of humanity and that no country can claim sovereignty over other planets. However, as private companies enter space exploration, the definition of ownership and the rights to exploit resources could lead to conflicts reminiscent of colonialism on Earth. Furthermore, the challenges of human settlement must be addressed. Colonizing another planet raises questions about governance, social structures, and the welfare of the settlers. How do we ensure that the new society reflects ethical treatment and respect for all? There must be guidelines to prevent abuses, whether they be environmental degradation or inequalities among colonizers. Ultimately, as we consider stepping into another world, we must learn from our history. Our approach should be rooted in respect and equity, promoting a future where space exploration enhances our understanding of the universe while honoring the delicate balance of life, wherever it may be found. The questions we ask now will shape not only our interplanetary endeavors, but also our ethical framework for generations to come. Researchers define habitable zones as regions around stars where conditions might be just right for life as we know it to exist. This zone is often referred to as the Goldilocks zone, named after the beloved fairy tale where things are not too hot, not too cold. The key factor in this zone is the distance from the star, which allows for liquid water to exist on a planet's surface, a critical ingredient for life. Too close to the star, and water boils away; too far, and it freezes solid. The habitable zone varies depending on the star's brightness and type. For example, the habitable zone around a smaller, cooler star like a red dwarf will be closer than the zone around a larger, hotter star like our Sun. Researchers have discovered that these zones can extend beyond just the classic planets we think of. Moons orbiting gas giants, known as exoplanets, are also considered for potential habitability if they reside in these welcoming spaces. Yet intriguing anomalies exist within these zones. Not all planets located in habitable zones are necessarily habitable. For instance, they may experience extreme weather, lack a protective atmosphere, or face intense radiation from their stars. Venus and Earth, both in the Sun's habitable zone, illustrate this well. While Earth is teeming with life, Venus is a cautionary tale, with its thick, toxic atmosphere and runaway greenhouse effect making surface conditions inhospitable. Researchers continue to refine their understanding of these zones, incorporating factors like a planet's atmospheric composition, climate stability, and magnetic field strength. As technology advances, astronomers are refining their searches for exoplanets within these habitable areas of the cosmos. There's a wondrous thrill in contemplating what civilizations or ecosystems might be out there, hidden within the vast expanses of these defined habitable zones. The question of whether extraterrestrial life exists captivates the imagination of many. On one side of the debate, proponents argue that the vastness of the universe strongly suggests the likelihood of life beyond Earth. There are billions of galaxies, each containing billions of stars, many of which have planets in their habitable zones, regions where conditions might support life. Given these staggering numbers, it seems statistically improbable that Earth is the sole cradle of life in the cosmos. Moreover, discoveries have been made in our own solar system that spark curiosity. For instance, the subsurface oceans of Jupiter's moon Europa and the salty lakes on Mars hint at environments where microbial life could potentially thrive. Scientists have also found extremophiles, organisms on Earth that survive in some of the harshest conditions, demonstrating that life can exist in environments previously thought to be uninhabitable. This indicates that life may be resilient and adaptable, raising further questions about where we might find similar forms of life elsewhere in the universe. However, the skeptics present compelling arguments as well. A central issue is the Fermi paradox, which ponders why, given the high probability of extraterrestrial civilizations, we have yet to encounter any evidence of them. Despite decades of searching through projects like the Search for Extraterrestrial Intelligence or SETI, we have not received any definitive signals or contact. This absence of evidence raises doubts about the existence of advanced life forms capable of communication or travel. Additionally, some argue from a perspective of biological uniqueness. They contend that Earth-specific conditions, ranging from its stable climate to the presence of water, are exceptionally rare. If life is as fragile as some believe, it could mean that intelligent civilizations are exceedingly rare or transient. This leads to the intriguing but sobering possibility that while microbial life may be common, complex beings capable of technology and communication might be far less frequent across the cosmos. These contrasting arguments ensure that the debate about extraterrestrial life remains lively and full of mystery. Extremophiles are remarkable organisms that thrive in the most hostile environments on Earth, from boiling hot springs to frigid ice and even deep ocean vents. These resilient life forms have significantly expanded our understanding of what constitutes a habitable environment. In the past, scientists believed that life could only exist under very specific conditions, usually temperate and lush. However, the discovery of extremophiles has reshaped this perspective, indicating that life can endure and even flourish in severe environments. This revelation has profound implications for astrobiology, the study of potential life beyond our planet. If life on Earth can thrive in such a range of extreme conditions, then it opens up possibilities for life on other planets and moons that we once deemed uninhabitable. For example, moons like Europa, with its icy surface and subsurface ocean, or Enceladus, which has geysers shooting water into space, are now considered prime candidates for exploring extraterrestrial life. If extremophiles can survive in icy depths or extreme salinities, who's to say that similar life forms couldn't exist in alien worlds? Moreover, the ability of extremophiles to resist radiation, high pressure, and temperature extremes challenges our assumptions about life's resilience. By studying how these organisms withstand such conditions, scientists can better understand the potential for life to exist in environments previously thought too inhospitable. For instance, researchers have isolated certain genes responsible for radiation resistance in extremophiles. These findings not only advance our understanding of life's limits here on Earth, but also guide our searches for life elsewhere. Extremophiles have expanded both the definition of what life can be and the types of environments capable of sustaining it. As we continue to explore our solar system and beyond, these tiny, resilient organisms remind us of nature's incredible adaptability and the many possibilities that the universe may hold for life beyond our own. Recent discoveries regarding the atmospheres of exoplanets have unveiled the potential for life beyond our solar system, sparking excitement within the scientific community. Advances in technology, particularly with space telescopes, have allowed astronomers to gather vital data from distant worlds. For instance, the James Webb Space Telescope has offered unprecedented insights into the composition and characteristics of exoplanetary atmospheres, revealing a complex tapestry of gases that could support life. One of the most fascinating findings involves the detection of water vapor in the atmospheres of several exoplanets. This is a critical indicator because water is essential for life as we know it. Notably, researchers have observed signs of carbon dioxide and methane as well, which are intriguing because they can be associated with biological processes. The presence of these gases in specific ratios can suggest the possibility of microbial life, functioning much like it does on Earth. Additionally, some studies have indicated the potential for atmospheres capable of sustaining temperature ranges conducive to life. For instance, planets located within the habitable zone of their stars, where conditions may allow for liquid water to exist, have been of particular interest. The discovery of chemical diversity in these atmospheres, including the potential for organic compounds, raises questions about the types of life that could develop in environments vastly different from our own. As we continue to probe exoplanetary atmospheres, we inch closer to answering the age-old question of whether we are alone in the universe. Each new finding cultivates a sense of wonder and possibility, as scientists discover not just the potential for life, but also the myriad ways life could manifest on planets circling distant stars. This ongoing exploration is not only deepening our understanding of the cosmos, but is also redefining what it means to be a habitable world. Isotopic signatures in meteorites serve as cosmic breadcrumbs that guide scientists in their quest to understand the origins of life beyond our planet. Meteorites, remnants from the early solar system, often contain unique isotopes, atoms of elements that have a different number of neutrons than their more common counterparts. These isotopes can tell us about the environments where these meteorites formed and the chemical processes that occurred there. One of the most intriguing aspects of isotopic analysis is its ability to reveal the building blocks of life. For instance, certain isotopic ratios of carbon or nitrogen can point to biological processes. On Earth, life tends to favor lighter isotopes, leading to distinct ratios in organic materials. By comparing these ratios in meteoritic samples, researchers can identify whether similar biological processes might have occurred elsewhere, perhaps even on other planets or moons. Moreover, the presence of certain isotopes can hint at the conditions of the early solar system and the potential for life's building blocks to form. Some meteorites contain amino acids, essential for life as we know it, that display isotopic signatures suggesting they may have formed in extraterrestrial environments. This raises fascinating questions about the delivery of organic materials to Earth via meteorite impacts, which could have played a pivotal role in the emerging biochemistry of our planet. Ultimately, studying isotopic signatures offers a glimpse into the cosmic history of our universe and its potential to harbor life. It allows scientists to piece together the story of not only where we come from, but also where we might find life beyond Earth, making meteorites invaluable time capsules from our solar system's past. The Fermi paradox poses a fascinating question. If the universe is vast and capable of supporting life, where is everyone? Given the billions of stars and potentially habitable planets in our galaxy alone, one would expect to see evidence of intelligent extraterrestrial civilizations. Yet we hear nothing, an enigmatic silence that has compelled scientists and thinkers to propose several theories. One of the leading ideas is the rare Earth hypothesis. This theory suggests that the conditions necessary for complex life are extremely rare in the universe. While simple life, like bacteria, may thrive in many cosmic environments, combining all the right factors, such as a stable star, the right planetary conditions, and a protective magnetic field, might be an extraordinary coincidence. This viewpoint posits that while simple life might be common, intelligent life is a rarity. Another possibility revolves around the concept of technological civilization's self-destruction. The Great Filter theory posits that at some point in their development, civilizations face challenges, such as nuclear war, climate change, or pandemics, that they cannot overcome. If most intelligent beings reach a stage where they either extinguish themselves or fail to develop advanced technology, this could explain our solitude in the cosmos. Additionally, some scientists speculate that highly advanced civilizations may prefer to remain undetected. This notion is linked to the zoo hypothesis, suggesting that other civilizations intentionally avoid contact with us, much like zookeepers trying not to disturb animals in their care. Perhaps they observe us from afar, or they might have ethical reasons for avoiding interference. Ultimately, these theories highlight the complexities of the universe and our place within it, leaving us to ponder if humanity is truly alone or merely a part of a quiet cosmos. The Drake equation is a fascinating tool that seeks to estimate the number of advanced civilizations in our galaxy with which we might be able to communicate. Formulated by astronomer Frank Drake in 1961, this equation incorporates several factors that reflect the conditions necessary for the emergence of intelligent life. At its core, the equation multiplies together various probabilities, such as the rate of star formation and the fraction of stars that have planets, to arrive at an estimated number of technological civilizations in the Milky Way. What makes the Drake equation particularly significant is not just its potential to provide a numerical answer, but also its ability to frame the scientific discussion around the search for extraterrestrial life. By breaking down the complex conditions for life into smaller, more manageable components, it guides researchers in identifying which aspects are understood and where knowledge gaps still exist. This encourages exploration and research in fields ranging from astronomy to biology, as each factor can prompt further investigation. The equation has inspired numerous scientific projects, including efforts like the Search for Extraterrestrial Intelligence, or SETI. Through radio telescopes and other observational means, SETI aims to detect signals from intelligent civilizations that may be out there, hidden amongst the stars. Each signal received, or not received, adds to our understanding of the variables within the Drake equation, refining our calculations and deepening our curiosity. Moreover, the Drake equation serves as a reminder of our place in the cosmos. It emphasizes not only the potential abundance of life, but also the uniqueness of our own existence. As we ponder the probabilities and possibilities of intelligent life elsewhere, we are compelled to reflect on our own civilization and the vast universe that surrounds us, bursting with mysteries yet to be uncovered. In the quest to understand our universe, scientists have stumbled upon several intriguing signals that some speculate may hint at extraterrestrial intelligence. One of the most captivating examples is the WOW signal, detected in 1977 by astronomer Jerry R. Amon while working on a SETI project at the Big Ear Radio Telescope in Ohio. This strong, narrowband radio signal lasted for 72 seconds and appeared to originate from the direction of the constellation Sagittarius, but its source has never been identified. The sheer intensity and unique frequency of the signal sparked excitement and speculation that it could represent a message from an alien civilization. Another fascinating phenomenon is the repeating fast radio bursts, or FRBs. These are brief, intense bursts of radio waves that last only a few milliseconds, but can release as much energy as the sun does in an entire day. Some of these bursts have been observed to repeat, leading scientists to search for their origins. While many FRBs have been traced back to natural astrophysical processes, such as magnetars and neutron stars, the potential for some of these signals to be artificial remains part of ongoing discussions in the scientific community. Additionally, the mysterious LGM-1 signals, discovered in the 1960s, also raised eyebrows. The term stands for Little Green Men, hinting at the parents' playful speculation about extraterrestrial life. These signals have since been attributed to pulsars, which are rapidly rotating neutron stars that emit beams of radiation. However, it lies in our nature to wonder if some signals may also mask their true origins, concealing a story waiting to be unraveled. Lastly, beyond radio waves, researchers have pointed to unexplained optical signals captured by telescopes. In 2017, a peculiar burst of light from a distant star, known as KIC 8462852 or Tabby's star, exhibited irregular dimming patterns that led to theories, including potential extraterrestrial megastructures. While further studies revealed more natural explanations, the ongoing search for signs of intelligent life adds layers of intrigue to our understanding of the cosmos. Each of these unexplained phenomena reminds us of the vastness of space and the possibilities that lie beyond our planet, keeping the human spirit of discovery alive. The study of interstellar microbes opens a fascinating window into the origins of life and how we understand it. Microbes, tiny organisms usually invisible to the naked eye, have been discovered in the vast emptiness of space. This raises profound questions about the resilience of life and its potential to exist beyond Earth. If life can withstand the harsh conditions of space, it suggests that life may be more common throughout the universe than we previously thought. One of the most compelling ideas emerging from this research is the notion of panspermia. This theory proposes that life could be transferred between planets through cosmic material, such as meteorites or comets. If microbes can survive the cold, vacuum, and radiation of space, they could potentially travel across vast distances and seed life on other planets. This possibility encourages scientists to rethink how life formed on Earth. Instead of being a unique event, the development of life might be part of a broader cosmic process. Moreover, understanding how these microbes survive in extreme environments provides insights into the conditions necessary for life to thrive. Studying their genetic adaptations and metabolic processes can illuminate the types of environments that would allow life to develop. This research can guide future missions to other planets and moons, as astrobiologists can target locations with similar extremophiles in mind. In short, interstellar microbes challenge our conventional views about the origins of life. They suggest that life's existence might not be a rare anomaly, but rather a widespread occurrence in the cosmos. As we continue to explore and uncover the mysteries of these resilient microorganisms, we deepen our understanding of life's beginnings, not just on Earth, but possibly across the universe. Europa, one of Jupiter's moons, stands out as a compelling candidate in the search for alien life due to several unique features. For starters, it has a thick ice shell covering a vast global ocean beneath. This ocean may hold more water than all of Earth's oceans combined. The presence of liquid water is a fundamental ingredient for life as we know it, making Europa an exciting place for astrobiologists to investigate. Moreover, scientists believe that the ocean may be in contact with Europa's rocky mantle, which can create the right chemical reactions necessary for life. This is similar to the hydrothermal vents found on Earth, where life thrives despite the absence of sunlight. The interaction between the ocean and the rock below could lead to a rich environment filled with organic compounds, which are essential for life's chemistry. Another intriguing aspect of Europa is its relatively young surface, characterized by long fractures and ridges. These features hint at geological activity, suggesting that the ice is constantly renewing itself. Such activity might provide a way for nutrients and energy from the ocean below to reach the surface, potentially creating an environment where life could exist. Additionally, Europa's thin atmosphere, primarily composed of oxygen, hints at processes that could allow energy exchange between the surface and the subsurface ocean. With upcoming missions like the European Space Agency's Jupiter Icy Moons Explorer and NASA's Europa Clipper set for the next few years, scientists are poised to gather more evidence. Each discovery could further illuminate the moon's potential as a cradle for extraterrestrial life, giving us fresh insights into our cosmic neighborhood. The Milky Way galaxy, our cosmic home, reveals a fascinating structure and composition that continue to intrigue astronomers. At its heart lies a bulge, composed primarily of older stars, which surrounds a supermassive black hole known as Sagittarius A star. This central region is densely packed and plays a crucial role in the dynamics of the galaxy. Surrounding this bulge is a flat, rotating disk, where most of the galaxy's gas, dust, and young stars are found. This disk is where the action happens, as it hosts vibrant star formation and swirling clouds of interstellar material. Moving outward, the Milky Way's spiral arms extend from the central disk, creating a stunning pattern that can be observed even from Earth. These arms are not merely static structures, they are dynamic features filled with young, hot stars and regions of intense star formation. They are also home to clusters of stars and nebulae, showcasing the beautiful diversity of stellar life. The stars within these arms are primarily young and bright, making them prominent light sources in the galaxy. Beyond the visible disk lies the halo, a more enigmatic and sparsely populated region that encircles the galaxy. The halo is made up of old stars and globular clusters, which are tightly packed groups of stars. This area also contains a significant amount of dark matter, a mysterious substance that we cannot see but whose gravitational effects shape the galaxy's structure. Dark matter is thought to make up a large portion of the Milky Way's total mass, influencing the orbits of stars and the dynamics of the entire galaxy. In addition to its structural components, the Milky Way's chemical composition adds to its peculiarities. It is a mix of elements forged in the cores of stars over billions of years. Heavier elements like carbon and oxygen, enriched through stellar evolution, are dispersed throughout the galaxy when stars explode as supernova. This process contributes to the ongoing cycle of star formation and further enriches the cosmic chemistry of our galaxy, influencing everything from the birth of new stars to the formation of planets capable of supporting life. The Milky Way is not just a collection of stars, it is a vibrant, ever-evolving ecosystem of astronomical phenomena. Globular clusters are fascinating celestial formations that present intriguing challenges to our typical understanding of galactic formation. These clusters are spherical collections of stars, often consisting of thousands to millions, that orbit the core of galaxies. What sets them apart is their striking age and density. Most globular clusters are believed to be some of the oldest objects in the universe, forming around 12 to 13 billion years ago. This considerable age suggests that they predate much of the surrounding galactic structure. Traditionally, galactic formation theories posited that galaxies develop through a process of gradual accumulation and merging of smaller structures over time. In this context, we would expect younger clusters that reflect the ongoing development of galaxies. However, the presence of these ancient globular clusters raises questions about their origins. They seem to have formed earlier than their host galaxies and did not undergo the same evolutionary processes. Instead of emerging from star formation within a galaxy, their characteristics suggest they may have formed independently before being captured into the galaxy's gravitational pull. Moreover, globular clusters are densely packed with stars that are predominantly old and metal-poor. In astronomy, metal is a term used to describe elements heavier than hydrogen and helium. These heavy elements are produced in the interiors of stars. If globular clusters had formed in the same environment as other stellar populations, we would expect to see a range of metallicities. Instead, the uniformity among globular clusters implies their stars formed in a different setting, possibly in the early universe before many stars had exploded and recycled metals into the surrounding space. These peculiarities push astronomers to reconsider simpler models of formation and think more dynamically about the history of our galaxy. The study of globular clusters encourages an exploration of a universe where initial conditions could lead to radically different development paths. They help illustrate the complex tapestry of cosmic evolution, where ancient structures continue to exist amidst the dynamic changes happening in galaxies today. The more we learn about these clusters, the more we uncover about the early universe and the processes that shaped it. Variable stars are a captivating category of celestial objects characterized by their changes in brightness over time. These fluctuations can occur for various reasons, from intrinsic factors in the stars themselves to extrinsic influences from their surroundings. Some variable stars pulse or expand and contract, while others may experience dramatic outbursts or eclipses from orbiting companions. This variability allows astronomers to glean insights into stellar life cycles and the underlying mechanics of our universe. One of the most intriguing aspects of variable stars lies in their diverse classifications. For instance, pulsating variable stars like Cepheid variables swell and shrink rhythmically. These stars are particularly important because they act as cosmic beacons, enabling astronomers to calculate distances to faraway galaxies with remarkable accuracy. On the other side of the spectrum, eruptive variable stars such as novae and supernovae offer profound mysteries surrounding stellar evolution and the explosive end of a star's life cycle. In addition to their scientific value, variable stars provoke questions about the dynamic nature of our galaxy. Some exhibit erratic changes in brightness that defy straightforward explanation, suggesting there is still much to learn. These irregularities can be influenced by factors such as magnetic fields or interactions with nearby stars. Each of these phenomena presents unique puzzles, urging scientists to continuously explore and refine their understanding of these celestial wonders. Furthermore, the study of variable stars is foundational in uncovering the history and structure of our galaxy. By mapping their locations and brightness, astronomers can identify stellar populations and assess the mass distribution of the Milky Way. This exploration not only expands our cosmic knowledge, but also deepens our appreciation of the intricate tapestry that composes our galaxy's narrative. The orbits of certain stars within our Milky Way galaxy can tell us a compelling story about the presence of unseen massive objects, particularly in the context of faint or invisible entities like black holes or dark matter. When astronomers observe these stars, they take careful note of their movement. Some stars, especially those located at the edges of our galaxy or near massive objects, exhibit unusual orbit patterns that suggest they are being influenced by the gravitational pull of something we cannot see. For instance, in regions where stars seem to be zipping around a central mass at high speeds, these motions can indicate the existence of a dense concentration of mass that cannot be directly observed. Take the area around the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. By tracking how quickly nearby stars orbit this invisible object, scientists have calculated its mass to be millions of times that of our Sun, even though it is hidden from view, illustrating just how powerful and significant unseen forces can be. In addition to individual stars, the collective movements of many stars can reveal the presence of dark matter, that mysterious substance that does not emit light or energy. The outer stars of the Milky Way have been found to move in ways that suggest there is more mass influencing their orbits than what we can see. This leads astronomers to conclude that a substantial amount of dark matter surrounds galaxies, creating a gravitational effect that shapes these movements. These observations are pivotal in piecing together the structure of our galaxy. By studying the motion of stars, astronomers can infer the existence of massive but unseen objects, broadening our understanding of the cosmos and challenging our perceptions of what is present in the universe. This ongoing investigation into star orbits links directly to greater mysteries, helping us comprehend not just our own galaxy, but the fundamental nature of the universe itself. The discovery of a cosmic void within our galaxy can significantly alter our understanding of the universe. A cosmic void is essentially a vast, empty region of space where the density of galaxies is remarkably low. When scientists identify such a void in our Milky Way, it raises intriguing questions about the structure and evolution of cosmic matter. These voids can serve as laboratories for studying the forces at play in the universe, helping us understand how the large-scale structure of the cosmos has formed over billions of years. One major implication of finding a void is the insight it provides into the distribution of dark matter. Generally, cosmic voids have a lower concentration of dark matter, which is crucial to the gravitational framework that holds galaxies together. By exploring these empty regions, scientists may gain information about how dark matter interacts and its role in shaping the galactic environment. This knowledge could refine existing theories on how galaxies evolve and move through the cosmic web. Additionally, uncovering a void within our galaxy could also impact our understanding of cosmic evolution. It might suggest that our galaxy, like others, has gone through processes that led to the formation of these large voids over time. This can challenge and enhance our theories about the uniformity and isotropy of the universe, suggesting regions that diverge from the average density of matter. These revelations can illuminate the past behaviors of galactic formations and helps clarify why some regions are richer in galaxies while others remain desolate. Lastly, the implications of such a discovery extend beyond just our galaxy. Understanding the dynamics and properties of cosmic voids contributes to the broader narrative of the universe's life cycle. By piecing together the information gleaned from voids, astronomers may develop strategies to interpret the large-scale structure of the universe more holistically, uncovering the fundamental principles that govern its expansion and the forces behind its evolution. Every void tells us a story about the universe and our place within it. Cosmic rays are high-energy particles that continuously bombard the Earth from outer space. They are primarily composed of protons, but can also include heavier atomic nuclei and electrons. When these cosmic rays strike the Earth's atmosphere, they can create a cascade of secondary particles in a phenomenon known as a cosmic ray shower. Studying these showers not only helps us understand the nature of cosmic rays themselves, but also reveals important information about our galaxy and the mysterious processes taking place within it. One fascinating aspect of cosmic ray showers is their ability to act as messengers from the depths of the universe. As cosmic rays travel across vast distances, they carry with them imprints of their origins. The energy levels of these particles can indicate various cosmic events, such as supernova explosions or interactions with black holes. By analyzing the characteristics of these showers, scientists can glean insights into the environments that produced them and how they contribute to the overall energy balance in our galaxy. Moreover, cosmic ray showers help identify areas of unusual energy or magnetic field activity in the galaxy. For example, if researchers observe an unexpected increase in high-energy cosmic rays from a specific region, it might signal unusual processes occurring there, such as the presence of a pulsar or other dense astrophysical objects. These anomalies challenge our understanding of cosmic phenomena, pushing scientists to refine existing models of galactic processes and explore new theories about the universe's workings. Additionally, cosmic ray studies can also provide information about the interstellar medium, the matter and radiation that exist in the space between star systems. Abnormalities in cosmic ray behavior can indicate variations in the density and composition of this medium, which plays a crucial role in star formation and the overall structure of our galaxy. Cosmic ray showers serve as a window into the dynamic and sometimes chaotic nature of our galactic environment, inviting scientists and enthusiasts alike to marvel at the ongoing discoveries they reveal. The Magellanic Clouds are fascinating celestial objects that hold a special place in the study of our galaxy. These two irregular dwarf galaxies, named the Large Magellanic Cloud and the Small Magellanic Cloud, are located just a few million light-years away from Earth, making them some of our closest galactic neighbors. Their proximity allows astronomers to observe them with remarkable detail, revealing unique properties that significantly enhance our understanding of the Milky Way. One intriguing aspect of the Magellanic Clouds is their role in the formation of new stars. Both clouds are teeming with young, vibrant stars and stellar nurseries where new stars are being born. They are also sites of intense stellar activity, including supernovae explosions. Studying these phenomena provides astronomers with valuable insights into the life cycles of stars, the processes of star formation, and the dynamics of stellar evolution, which can, in turn, shed light on our own galaxy's history. Another compelling feature of the Magellanic Clouds is their gravitational interaction with the Milky Way. These galaxies are not simply passive objects. They are in a delicate dance with our galaxy, influenced by its gravitational pull. Over time, the Magellanic Clouds have been observed to lose gas and stars to the Milky Way, creating spectacular tidal tails of stars and gas that trail behind them. This interaction helps scientists understand how galaxies evolve and interact, offering a glimpse into the processes that shaped our own cosmic neighborhood. Finally, the Magellanic Clouds serve as a natural laboratory for studying dark matter. The distribution of stars and gas within these galaxies suggests the presence of an unseen component that affects their motion and structure. By analyzing these dynamics, astronomers can better grasp the role of dark matter in galaxy formation and evolution. The Magellanic Clouds are not just captivating objects in the sky, they are vital keys to unlocking the mysteries of our universe. Mapping the Milky Way is an incredibly complex task, primarily because we're trying to chart a galaxy from within it. Imagine being inside a large, foggy city and trying to draw a map of it without a clear view from above. The vastness of the Milky Way spans about 100,000 light-years across, and with billions of stars, our location within it makes it difficult to see the whole picture clearly. Scientists utilize a variety of tools and techniques, including telescopes and satellite measurements. But obstacles such as dense cosmic dust can obscure our line of sight, making it hard to gather data on distant stars. Another significant challenge arises from the sheer scale and dynamics of the galaxy itself. Different regions of the Milky Way rotate at different speeds, complicating matters further. This varying rotation means that stars and clusters we observe may not be where we think they are when we consider their movement over time. Additionally, the gravitational influences of massive objects, like black holes and clusters of stars, can distort our measurements, leading to potential misestimations of distances and positions within the galaxy. Anomalies such as unexpected star formations and the presence of dark matter also pose intriguing challenges. Dark matter makes up a substantial portion of the Milky Way's mass, but cannot be seen directly. Instead, scientists infer its presence through gravitational effects on visible matter. These gravitational influences can create peculiar patterns in the distribution of stars, which raises questions about the structure of the galaxy. Understanding how dark matter interacts with normal matter plays a critical role in refining our maps. Despite these obstacles and mysteries, scientists persist in their quest to navigate the Milky Way's complexities. With advancements in technology, including space observatories and improved computational models, researchers continue to unveil new insights about our cosmic home. Each anomaly or challenge encountered adds to our understanding, painting a richer picture of the universe and inviting us to explore even deeper into the night sky. Rogue stars are celestial bodies that wander through space without being bound to any specific galaxy. Their existence, once considered unusual, has significantly expanded our understanding of galactic dynamics. Initially, scientists believed that stars formed in clusters and stayed within their birth galaxies. However, the discovery of rogue stars has shed light on the complex interactions and processes that can lead to a star being ejected into intergalactic space. One of the most intriguing aspects of rogue stars is how they can result from gravitational interactions. When two stars or a star and a black hole collide or pass closely together, one might gain enough energy to escape the gravitational pull of its galaxy. This insight has changed the way astronomers view stellar formation and interactions, illustrating that stellar life is not confined to the boundaries of galaxies. The study of rogue stars also helps scientists understand the broader structure of galaxies. By studying these solitary travelers, researchers can gather information about the mass distribution in galaxies and the effects of dark matter. These rogue stars act as cosmic messengers, providing clues about their galactic origins and the dynamics of stellar movements. Their peculiar trajectories can reveal hidden gravitational influences that are not visible through conventional methods. Additionally, rogue stars can illuminate the processes of galaxy formation and evolution. As researchers track the paths of these stars, They can better understand how galaxies interact and merge over cosmic timescales. The study of rogue stars has enriched our comprehension of the cosmic dance of galaxies, highlighting the dynamic and ever-changing nature of the universe. This continuing exploration teaches us that the universe is filled with surprises, often from the most unexpected sources. Binary systems, where two stars are locked in orbit around each other, play a crucial role in our understanding of cosmic anomalies in our galaxy. These pairs of stars can reveal significant insights into stellar evolution, the nature of gravity, and even the physics of black holes. When studying these systems, astronomers can observe how the stars influence each other, which can shed light on their masses, ages, and evolutionary pathways. One of the most fascinating aspects of binary systems is their ability to provide precise measurements of star masses. By observing how the stars orbit one another, scientists can apply Kepler's laws of motion to calculate their masses with remarkable accuracy. This information is essential in establishing models for stellar formation and evolution. In a galaxy that is continually changing, understanding how these stars interact helps fill in the gaps regarding stellar life cycles and the formation of various cosmic structures. Binary systems can also serve as natural laboratories for studying more exotic objects, such as neutron stars and black holes. When one star in a binary pair reaches the end of its life, it can explode as a supernova, leaving behind either a neutron star or a black hole. If the remaining companion star is close enough, it can begin to accrete material from the deceased star, resulting in fascinating and complex phenomena. These interactions can lead to observable events like X-ray bursts, which provide critical data for astronomers attempting to understand high-energy processes in our universe. Additionally, observing how binary systems respond to cosmic anomalies, such as gravitational waves, a ripple in the fabric of space-time caused by massive celestial bodies accelerating, has revolutionized our comprehension of the universe. When two black holes or neutron stars merge, the resulting gravitational waves can travel across vast distances, helping us map the origin of such events and confirm theories surrounding gravity. In this way, binary systems are not only pivotal for understanding individual stars, but also serve as vital touchpoints in the broader narrative of our galaxy and beyond. Cultural interpretations of the cosmos significantly shape how societies understand the universe and influence the approach scientists take when investigating anomalies. Throughout history, various cultures have held unique views about the night sky, imbuing celestial phenomena with spiritual or mythological meanings. For instance, ancient civilizations often connected star formations and planetary movements to divine messages or agricultural cycles. These narratives framed early scientific questions and inquiries, guiding scholars in their quest for knowledge. As modern science emerged, particularly during the Enlightenment, many societies began to distinguish between scientific understanding and cultural beliefs. However, remnants of these earlier interpretations persist. When scientists encounter unusual phenomena, the context of cultural beliefs can encourage diverse hypotheses, blending the lines of scientific inquiry with cultural narratives. For example, consider how unexplained events like the appearance of a comet could lead different cultures to interpret them as omens, while researchers might approach the same event through a scientific lens, seeking explanations involving the object's composition or trajectory. Moreover, the influence of cultural interpretations can drive research priorities and funding, directing attention to certain anomalies perceived as more significant or interesting based on societal views. When something occurs in the sky that captures the public's imagination, like a supernova or an unexplained astrophysical event, scientists may find themselves addressing not just the scientific questions, but also the cultural narratives surrounding these occurrences. This layered approach can lead to a richer understanding of both the phenomena and its wider impact on society. Ultimately, engaging with cultural interpretations offers a unique perspective, reminding us that scientific inquiry does not exist in a vacuum. It unfolds within a tapestry of human experience, history, and shared understanding. By considering these factors, scientists can approach anomalies not only as puzzles to be solved, but as integral parts of the human story that enrich our journey to comprehend the cosmos. The discovery of other galaxies and even the potential existence of multiple universes invites profound philosophical questions that reach deep into our understanding of existence itself. For instance, if our galaxy is just one among countless others, what does that imply about the significance of humanity? Are we alone in the cosmos, or do other intelligent beings exist out there? These questions challenge our notions of identity and purpose, prompting us to consider whether our experiences and values hold meaning in the vastness of space. Furthermore, the concept of parallel universes raises intriguing ideas about reality. If there are other universes with different laws of physics or alternative histories, it leads us to ponder the nature of our own universe. What does it mean for our understanding of fate and free will? If every possible outcome exists in some universe, how does that affect our choices and the meaning of our actions? These questions push us to reconsider the relationship between chance and destiny in our lives. Additionally, the existence of multiple galaxies and universes can invoke a spiritual or existential contemplation. What role does humanity play in a universe filled with such diversity? This line of inquiry can lead to a re-evaluation of religious beliefs and concepts of creation, urging us to explore the intersection of science and spirituality. As we expand our view of the cosmos, our understanding of existence may shift, leading to new philosophical paradigms that help frame our place within the universe. The discovery of other galaxies and the speculative nature of multiple universes invite us to explore deep philosophical questions about existence, reality, and meaning. Each new finding in the cosmos opens a pathway for reflection on our human condition, our place in a much larger narrative, and the ideas we hold about what it means to be alive in this vast and mysterious universe. Time is a fascinating concept in cosmology, playing a crucial role in how we understand the universe. In classical physics, time is often viewed as a constant, a linear progression from past to present to future. This straightforward view allows us to think of time as a universal clock that ticks the same for everyone, everywhere. However, as we delve deeper into the cosmos, particularly through the lens of relativity, we discover that this notion of time becomes far more complex and intriguing. Albert Einstein's theory of relativity introduced the idea that time is linked to space, creating a continuum known as spacetime. According to this theory, time can dilate or stretch depending on the speed at which an object is moving and the gravitational field it is experiencing. For example, an astronaut traveling near the speed of light would age more slowly than someone on Earth due to the effects of time dilation. This suggests that time is not an absolute entity, but a relative one, experienced differently depending on one's position and motion within the universe. In contrast, quantum mechanics presents another layer of complexity to the concept of time. Here, time may not be as simple as a river flowing in one direction. The foundational principles of quantum theory imply that time might not always move linearly. Events at the quantum level can appear to be interconnected in ways that defy the typical progression we associate with time. This raises questions about causality and whether time itself could be perceived differently at fundamental levels of reality. Moreover, certain cosmological models, such as those involving the Big Bang or the cyclical universe, challenge our traditional views of time altogether. In the Big Bang model, time itself began with the explosion of energy that birthed our universe. Before that moment, the concept of time as we know it may not have even existed. Other models suggest that the universe could go through endless cycles of expansion and contraction, suggesting a different kind of temporal experience. Through these various cosmological lenses, we see that time is not simply a backdrop for cosmic events. Instead, it is a dynamic and integral element that shapes our understanding of the universe itself. The search for extraterrestrial civilizations is filled with both fascination and ethical complexity. One of the primary considerations is how to responsibly approach and interact with these potential life forms, should we find them. Scientists grapple with questions about the impact of our messages or signals, like the famous Arecibo message sent into space. What responsibilities do we hold when announcing our presence to the universe? There is a fear that reaching out could attract unwanted attention, much like a signal in the night might draw predators. Another core ethical consideration revolves around the potential exploitation of any discovered civilizations. If a more technologically advanced species is found, there is a concern about our intentions. Would we treat them as equals? or would there be a temptation to manipulate or utilize their resources? Scientists question whether humanity is prepared for an encounter with a civilization vastly different from us, and whether we possess the ethical framework to engage with them respectfully. Equally challenging is the potential for human bias in judging other forms of life. Scientists worry about the tendency to judge extraterrestrial civilizations against our own moral and cultural standards. This can lead to misinterpretations of their actions or intentions. There's a growing recognition that diversity in intelligence and culture could take forms we can't yet imagine, and our ethical responsibility is to keep an open mind while being careful not to impose our values onto others. Finally, when considering the implications of discovering extraterrestrial life, there is a profound existential question that arises. How would such a discovery change our understanding of ourselves and our place in the universe? The implications could be transformative, reshaping everything from philosophy to religion. Thus, scientists walk a tightrope, balancing the excitement of discovery with the heavy weight of ethical considerations, always asking how best to proceed in a vast cosmos teeming with possibilities. Our understanding of the universe has a profound impact on human consciousness and culture, shaping our beliefs, philosophies, and even our scientific pursuits. Throughout history, the cosmos has inspired countless artistic expressions and theological reflections. From the ancient Greeks gazing at the night sky, pondering the stars as deities, to Renaissance artists incorporating celestial themes in their works, the universe has always captivated the human imagination. It raises fundamental questions about our existence and our place within the vastness of reality. As we have gained knowledge through science, our view of the universe has shifted dramatically. With the advent of telescopes and later space missions, we began to see the cosmos as a dynamic and ever-evolving entity, rather than a static backdrop to human life. Consider how the discovery of the Big Bang theory changed our understanding. It suggested that the universe has a beginning and implies a sense of interconnectedness among all forms of matter and energy. This idea has seeped into philosophical discussions, influencing modern existential and ecological thought. Moreover, the realization that our planet is just a small speck in a vast universe has also shaped cultural narratives and societal values. It encourages a sense of humility and responsibility towards our environment. Scientific findings about climate change, for example, have led to a rising global consciousness about sustainability and our impact on Earth's ecosystems. This awareness is changing the way we live and interact with our planet, fostering movements that prioritize compassion for all living beings. In a sense, our exploration of the universe encourages us to transcend our individual concerns and think collectively. The very act of seeking answers about the cosmos helps cultivate a shared sense of wonder and curiosity. It acts as a unifying force across diverse cultures, reminding us that regardless of our differences, we all share the same sky. This intersection of science, art, and philosophy creates a rich tapestry of human culture, shaped by our ongoing quest to understand our universe and, in turn, ourselves. Philosophical perspectives play a significant role in shaping our understanding of cosmic mysteries. Throughout history, thinkers have pondered questions about existence, the nature of the universe, and our place within it. This philosophical inquiry intersects beautifully with cosmology, offering rich frameworks that help us interpret the vast and often unfathomable phenomena of the cosmos. For instance, the age-old philosophical question of why there is something rather than nothing invites scientific exploration while simultaneously eliciting deep existential reflection. Cosmologists work to understand the origins of the universe, leading us to concepts such as the Big Bang. However, philosophical perspectives encourage us to consider the implications of such discoveries and what they mean for humanity. This interplay between science and philosophy opens a dialogue about the limits of human understanding and the questions that may forever elude our grasp. Moreover, different philosophical traditions provide unique lenses through which we can view cosmic phenomena. Eastern philosophies, such as Buddhism, emphasize the interconnectedness of all things, which resonates with modern scientific ideas in quantum physics and the fabric of space-time. Meanwhile, Western thought often wrestles with the dualities of mind and body, which can influence how we interpret consciousness in relation to the universe. This diversity in philosophical thought enriches our understanding and allows for a more nuanced appreciation of cosmic mysteries. Ultimately, the marriage of philosophy and science provokes deeper questions and insights into our existence. While scientists gather empirical evidence to build our knowledge of the universe, philosophers remind us to engage with the why behind those facts. This partnership fosters a holistic understanding that not only satisfies our curiosity, but also nurtures our wonder about the cosmos and our role within it. As we explore the universe, the blending of philosophical inquiry with scientific discovery invites us to dream, reflect, and ultimately find meaning amid the stars. The concept of infinity has fascinated thinkers for centuries, and it plays a crucial role in our understanding of space and cosmic anomalies. When we look into the vastness of the universe, we encounter the idea that space itself may be infinite. This notion challenges our perception of boundaries and limits, leading to profound questions about what lies beyond the edges of our observable universe. Astronomers have detected mysterious phenomena, like black holes and dark matter, that force us to reconsider the nature of infinity. Black holes, with their immense gravitational pull, create regions in space where conventional rules seem to break down. At the event horizon, the point of no return, time itself behaves strangely. If we imagine a traveler approaching this boundary, they would experience time differently than someone observing from a safe distance. This highlights how infinity can distort our understanding of time and space. Additionally, the very structure of the universe pushes our comprehension of infinity to its limits. Scientists theorize about the multiverse, where countless other universes could exist alongside our own, each with different laws of physics. If true, this scenario would expand our conception of infinity beyond just the space we can see into boundless realms that elude our understanding. Understanding cosmic anomalies, such as the expanding universe, also ties back into infinity. As the universe expands, it raises questions about whether it will continue on indefinitely or eventually reach a state of equilibrium. The idea that space might go on forever suggests that we are just a tiny fragment of something vastly larger. This perpetual exploration into the nature of infinity keeps our curiosity ignited as we strive to uncover the very secrets of existence itself. The portrayal of space in art and literature has profoundly shaped public perception of scientific discoveries throughout history. From ancient mythologies to contemporary science fiction, these artistic expressions ignite our imagination and enrich our understanding of the vast universe. They allow us to explore complex ideas about the cosmos in a way that is both accessible and emotionally resonant, transforming what might seem like abstract concepts into relatable narratives. Consider the impact of famous works like Jules Verne's From the Earth to the Moon. Written in the 19th century, this novel captured the public's fascination with space travel long before actual rockets were developed. It not only entertained but also inspired a collective belief in the possibility of human journeys beyond Earth. Similarly, the enchanting images painted by artists like Vincent van Gogh in Starry Night evoke a sense of wonder about the night sky and our place within it, fostering a curiosity that drives scientific exploration. Moreover, films and television series, such as Stanley Kubrick's 2001: A Space Odyssey, have played crucial roles in popularizing and visualizing scientific advancements. These mediums introduce audiences to complex concepts in a digestible format, often encouraging public discourse around space exploration. Such representations can sometimes inspire technological advancements themselves, as they prompt scientists and engineers to turn what was once fiction into reality, thus closing the gap between science and imagination. Furthermore, art and literature often address the philosophical and existential questions posed by our exploration of space. They capture the thrill of discovery and the emotional challenges of confronting the unknown. By framing scientific discoveries within human stories, they invite us to reflect on our aspirations and fears regarding the cosmos. This interplay between creativity and science enriches the public's understanding, making the mysteries of space feel not just like facts and figures, but parts of a much larger human narrative. Space anomalies, those mysterious phenomena that challenge our understanding of the universe, can provoke deep philosophical questions about fate and free will. When we look at the cosmos, we see a framework of laws and forces, from gravity to the spinning of galaxies. These elements can suggest a predestined path, where events unfold according to set patterns. However, the existence of anomalies like black holes or the peculiar behavior of dark matter introduces an element of unpredictability that complicates this notion. Consider how black holes warp space-time. They can heat up surrounding matter to extreme temperatures, and their gravitational pull can alter the trajectories of nearby stars. Such phenomena can seem to dictate the fate of celestial bodies, leading us to ponder whether any entity, be it a star or a human being, has true control over its path. If the universe contains centers of such immense manipulation, does it lessen our sense of agency? Or does it merely invite us to explore how we navigate choices within a grand design? On the flip side, these anomalies also represent the unexpected, the discovery of new paths within the cosmos. When scientists encounter something unexplainable, it can inspire innovation and a fresh approach to understanding. This invites a perspective that free will isn't just about making choices, it's also about responding to the unpredictable nature of existence. The universe, with all its quirks, offers a canvas where the paint can be splattered in surprising ways, leaving room for individual action and creativity within the chaos. In this ongoing dance between the structured laws of physics and the unpredictable nature of space anomalies, we find a reflection of our own lives. Just as stars may encounter unforeseen events that change their trajectories, we too navigate through a world filled with uncertainties. Each decision feels deeply personal, yet we are also influenced by the vast and complex web of circumstances around us. Perhaps in recognizing the anomalies in space, we can find parallels in our quest for understanding fate and free will, suggesting that while destiny may set the stage, our choices shape the narrative. Cultural beliefs about the cosmos have played a significant role in the way we understand our universe today. Each civilization has its own stories and interpretations, reflecting their unique experiences and environments. For instance, ancient civilizations viewed the stars as gods or ancestors, leading to a deep sense of connection between their lives and the cosmos. Even today, many cultures hold on to traditional beliefs that influence their understanding of astronomical phenomena. As modern science has advanced, these diverse cultural perspectives continue to inform scientific dialogues. Today's cosmology is not only shaped by mathematics and observations, but also enriched by philosophical inquiries rooted in historical narratives. The way people perceive concepts like time, space, and existence can vary widely. This rich tapestry of beliefs encourages scientists to engage in interdisciplinary conversations that incorporate both scientific and cultural views, allowing for a more holistic understanding of our universe. Moreover, the dialogue between science and culture can foster greater inclusivity in the field of astronomy. By acknowledging and respecting different cosmological beliefs, scientists can reach out to broader audiences. This connection can encourage younger generations from various backgrounds to pursue careers in science, inspiring them to explore the mysteries of the universe through their own cultural lenses. In this way, cultural narratives not only coexist with scientific inquiry, but actively shape its evolution. In the end, the intersection of diverse cultural beliefs with modern scientific dialogues highlights the complexity of humanity's quest for understanding. It invites us to celebrate the richness of our shared curiosity, reminding us that science is not just a pursuit of knowledge, but also a shared journey through the universe that resonates deeply with our varied human experiences. Astrophysics, the study of the universe and its phenomena, is a vast field filled with intriguing mysteries. Even with the remarkable advancements in technology and knowledge, many questions still puzzle scientists. One of the most pressing inquiries revolves around dark matter and dark energy, which together make up about 95% of the universe. Researchers are striving to understand what these components are, as they don't emit, absorb, or reflect light. Their elusive nature raises fundamental questions about the very fabric of the cosmos. Another significant question centers on the existence of life beyond Earth. Despite decades of searching, scientists have yet to find definitive evidence of extraterrestrial life. This quest leads to intriguing hypotheses about the conditions required for life and whether intelligent civilizations might exist elsewhere in the universe. The exploration of planets in our solar system, such as Mars and the moons of Jupiter and Saturn, continues to be a focal point in this quest. The more we learn about these celestial bodies, the better we understand the potential for life beyond our own planet. A third area sparking intense curiosity is the mystery of black holes. While we have made strides in understanding their formation and properties, many questions remain. For instance, what happens to information that falls into a black hole? This dilemma, often referred to as the information paradox, challenges our understanding of the laws of physics and the nature of reality itself. Scientists are constantly delving deeper into gravitational waves and other phenomena to unlock more secrets of these cosmic giants. Lastly, there is the overwhelming question of the universe's fate. Will it continue to expand indefinitely, or will it ultimately collapse? The nature of cosmic expansion and its implications for the future of galaxies, stars, and planets is a topic of great debate. As researchers gather more data from distant galaxies and refine their models, they inch closer to unraveling these mysteries. Each answer brings with it new questions, keeping the field of astrophysics vibrant and full of wonder. The universe is a vast and enigmatic place, and our understanding of it is far from complete. Each day, scientists are making new discoveries that challenge our existing paradigms. For instance, the detection of gravitational waves marked a monumental shift in astrophysics, confirming predictions made by Albert Einstein a century ago. Such breakthroughs not only deepen our understanding of cosmic events, like black hole collisions, but they also prompt us to reconsider the fabric of space and time itself. As we continue to explore the cosmos, advancements in technology and instrumentation are likely to reveal phenomena we currently cannot even imagine. The ongoing study of dark matter and dark energy, which together make up around 95% of the universe, could dramatically alter our cosmic models. We know so little about these fundamental aspects, and uncovering their nature could lead to new theories that redefine our view of everything from galaxy formation to the ultimate fate of the universe. Moreover, the discovery of exoplanets within habitable zones of their stars suggests that life beyond Earth may be possible. If we were to find microbial life or even intelligent beings, that would revolutionize our perspective on life's uniqueness and place in the cosmos. It would foster profound questions regarding the interconnectedness of all life and how we define existence. Lastly, as we probe deeper into the cosmic background radiation and the very origins of the universe itself, we might encounter evidence that prompts a complete overhaul of our current cosmological models. Each new piece of evidence encourages fresh theories, sometimes affirming our existing beliefs, and at other times compelling us to rethink everything we thought we knew about the nature of reality. The future of cosmology holds endless possibilities for discovery, promising to reshape our understanding in ways we are only beginning to fathom. As we journey through life, our personal experiences tend to shape the way we view the cosmos. Consider the quiet, winding paths of a favorite park, where the rustling leaves gently remind us of the cycles of nature. Those moments spent in solitude can inspire profound thoughts about our place in the universe, sparking curiosity about the stars above and the distances that separate us. An experience like stargazing on a clear night can illuminate the mysteries of the cosmos in a most beautiful way. Imagine lying on a blanket under a vast sky, the Milky Way arching overhead like a shimmering river of light, causing one to ponder the billions of stars that comprise it. Each point of light represents a sun, and with every glance upward, it becomes easier to appreciate the immense scale and complexity of the universe. Personal encounters with science, be it a captivating book, an enlightening documentary, or a thought-provoking lecture, can also play a pivotal role in shaping one's perspective. These experiences can open doors to a new understanding, revealing the underlying principles that govern everything, from the tiniest atom to the largest galaxy. Each insight can deepen our appreciation for the universe's wonders, transforming curiosity into a thirst for knowledge. In the end, it's often a blend of these encounters, each shaping our understanding like layers of sediment in a geological formation. As we reflect on our experiences, moments of awe, discovery, and even confusion, we find that they encourage us to keep asking questions. In this journey of exploration, we are drawn ever closer to understanding the breathtaking mysteries held within the vast expanse of space. Public interest in space exploration can be a delicate balance of education, engagement, and inspiration. To maintain this interest amid the rapid pace of scientific discovery, it is crucial to highlight the tangible benefits that space research brings to daily life. For instance, innovations developed from space technology have led to advancements in telecommunications, healthcare, and even weather forecasting. By showcasing these real-world applications, the public can better understand how space exploration directly affects them. Engaging storytelling plays a vital role in sustaining public support. Humanizing the journey of scientists and astronauts can foster a personal connection to space missions. By sharing compelling narratives about the challenges faced in outer space, the triumph of human ingenuity, and the story of those who dedicate their careers to exploring the unknown, we can capture hearts and minds. Efforts to include diverse voices and experiences in these stories further enhance relatability and broaden public appeal. Moreover, hands-on experiences can be a powerful way to stoke interest. Interactive exhibits, virtual reality experiences, and community events allow the public to engage with space exploration in meaningful ways. Educational initiatives, particularly in schools, can ignite the imagination of young minds, fostering a future generation that is both knowledgeable and passionate about the cosmos. By involving communities in the exploration process, we create a more invested public. Lastly, robust communication from space agencies, scientists, and educators is essential. Regular updates about missions, discoveries, and upcoming events can keep the thrill alive. Social media platforms serve as an effective medium for sharing visually arresting content and breakthrough discoveries, while community outreach programs can spark conversations around the significance of exploring the universe. Ultimately, weaving together inspiration, education, and personal connection can sustain a vibrant public interest in the wonders of space exploration. Exploring space anomalies is a pursuit that transcends individual achievements and taps into our collective curiosity about the universe. The legacy I hope to leave is one of inspiration, igniting the imaginations of future generations to wonder about their place in the cosmos. When young minds are exposed to the mysteries of black holes, dark matter, and other cosmic phenomena, it nurtures a sense of inquiry that can lead to groundbreaking discoveries and innovations. Additionally, I envision a legacy that emphasizes collaboration and curiosity across disciplines. The study of space is not just about astronomy, it involves physics, chemistry, and even philosophy. This interconnectedness allows for a richer understanding of our existence. By advocating for interdisciplinary approaches, I hope to encourage future scientists, artists, and thinkers to work together, breaking down silos and producing holistic insights about our universe. Moreover, I wish for this legacy to instill a sense of stewardship for our home planet. As we gaze at the infinite cosmos, we are reminded of the fragility of Earth. By highlighting how space anomalies can provide insights into our planet's history and future, I hope to cultivate a responsible approach to science and conservation. Ultimately, the legacy lies in understanding that our pursuit of knowledge should enrich life on Earth and promote a sustainable future. In conclusion, the goal is not merely to add to the body of scientific knowledge, but to inspire wonder, promote collaborative exploration, and encourage a sense of responsibility for our world. The inquiries into space anomalies can pave the way for a brighter, more interconnected future, where curiosity leads the way.